Welcome to The Chill Scientist. Comment a science topic you'd be interested in learning more about. Let's jump right in. Unlike the planets visible to the naked eye, Neptune remained hidden from humanity for most of history. Its faint light was too dim to stand out among the countless stars in the night sky. The discovery of Neptune in 1846 was not the result of chance observation, but a triumph of mathematics, prediction, and persistence. In fact, it is often regarded as one of the most remarkable achievements in the history of astronomy. The story begins with Uranus. When William Herschel discovered Uranus in 1781, astronomers carefully charted its orbit. Over time, they noticed that Uranus did not always move as Newton's laws of gravity predicted. Small deviations in its orbit suggested that some unseen force was tugging at it. These irregularities were subtle but persistent, and they could not be explained by measurement errors alone. By the early 19th century, the idea emerged that perhaps another, more distant planet was disturbing Uranus's path. Two mathematicians working independently took on the challenge. In France, Urbain Le Verrier calculated where this hypothetical planet must be. At nearly the same time in England, John Couch Adams was conducting similar work. Both men applied Newtonian mechanics with remarkable precision, estimating the mass, distance, and position of the mystery planet based solely on its gravitational effects on Uranus. The idea that mathematics alone could point to the existence of an unseen world was bold, but the reasoning was sound. Le Verrier's predictions were presented to Johann Galle, an astronomer at the Berlin Observatory. On the night of September 23, 1846, Galle and his assistant Heinrich de Rest turned their telescope to the region of the sky that Le Verrier had identified. Within a single degree of the predicted position, they found a faint disc-like object that shifted against the background stars. It was Neptune. This was the first time in history that a planet had been discovered not by direct observation, but by calculation. The discovery sparked both celebration and controversy. French astronomers hailed Le Verrier as the discoverer, while English supporters argued that Adams deserved equal credit. Today, history acknowledges that both men made important contributions, though it was Le Verrier's prediction that directly led to the observation. Regardless of the national disputes, the discovery of Neptune stands as a testament to the power of mathematics and Newton's theory of gravitation. The cosmos, once thought to be unknowable except through observation, could now be revealed through calculation. Neptune's discovery also had symbolic importance. It showed that the universe operated according to predictable laws, and that human reasoning could extend beyond what the eye could see. This moment reinforced confidence in science. During a century already marked by revolutions in physics, chemistry, and biology, Neptune was not just a new planet. It was proof that the human mind could uncover hidden truths about the cosmos through logic and perseverance. Interestingly, Neptune had actually been observed before 1846, but never recognized for what it was. Galileo himself sketched Neptune in 1612 and 1613, when it appeared near Jupiter in the sky. However, he mistook it for a fixed star because it was so dim and slow-moving. Other astronomers in the 18th century also recorded Neptune without realizing it was a planet. These accidental observations make the 1846 discovery even more striking. Neptune had been in plain sight, yet it took the combination of mathematics and careful observation to claim it. The triumph of Neptune's discovery left astronomers with renewed curiosity. If Uranus's irregularities could reveal Neptune, could further anomalies point to yet another hidden planet? This line of thinking would eventually fuel the search for Planet X, leading to the discovery of Pluto in 1930. But Neptune's case remains the gold standard of prediction fulfilled. The night when equations written on paper became a new world in the sky. Once the new planet had been confirmed in 1846, astronomers quickly faced a question of identity. What should this distant world be called? Unlike the ancient planets known since antiquity, which already carried names rooted in mythology, Neptune was the product of a modern, calculated discovery. Its naming became a blend of tradition, politics, and symbolism. Initially, there was no agreement. Some British astronomers suggested naming the planet after John Herschel, the son of William Herschel, who had discovered Uranus. Others proposed names tied to monarchs, such as Leverrier's planet, in honor of the French mathematician whose calculations had guided the discovery. In fact, for a short time, some in France attempted to push for the official adoption of Leverrier as the planet's permanent name. This echoed the earlier attempt to name Uranus Georgium Sidus, after King George III, which had also been unpopular outside Britain. The international scientific community resisted repeating that mistake. The tradition of naming planets after mythological figures provided the solution. Since Uranus had been given a name drawn from Greek mythology, it made sense to continue with the Roman pantheon for consistency. Johann Galle, the astronomer who had first identified Neptune through his telescope, favored this approach. The name Neptune, the Roman god of the sea, was proposed and quickly gained broad acceptance across Europe. The choice was fitting. The planet's deep blue color, caused by methane absorption in its atmosphere, evoked images of the ocean. The association with water and the sea god made the name particularly symbolic. Neptune's trident became a natural emblem for the planet, just as Saturn was represented by the sickle and Mars by the spear. This continuity of mythological symbolism helped integrate Neptune into the existing framework of planetary names, maintaining the sense of cosmic order that astronomers and the public alike found appealing. There were, however, a few competing suggestions. Some preferred Janus, the Roman god of transitions, to reflect Neptune's role in expanding the solar system's boundaries. Others considered Oceanus, a Greek titan associated with the waters of the world. But Neptune carried the strongest resonance, and by the late 1840s, it had become the accepted name across scientific circles and eventually in public imagination. The adoption of Neptune's name reinforced a pattern. Each new planet discovered was linked to mythology in a way that reflected its place in the solar system. Uranus represented the sky, Saturn his son who overthrew him, Jupiter the king of the gods, and Neptune, the ruler of the seas, as the next outward. Symbolically, Neptune's position in the solar system was like the vast ocean at the edge of known lands, distant, mysterious, and powerful. The mythological choice also carried cultural weight. The mid-19th century was a time of rapid change, marked by industrial progress and expanding global exploration. Naming the new planet after the god of the sea connected the excitement of space discovery with the familiar imagery of ocean voyages. Just as sailors had once pushed across unknown waters to discover new continents, astronomers were now extending human knowledge across the cosmic ocean. Even today, the name Neptune shapes how we imagine the planet. The deep azure of its clouds, the violent storms that churn through its atmosphere, and the icy winds that roar around it all seem fitting for a world tied to the ancient god of the seas. The myth has become entwined with the science, reminding us that astronomy is not just about data and equations, but also about meaning, story, and the human drive to place the unknown within a framework of understanding. Neptune is the 8th and most distant planet in our solar system, orbiting about 4.5 billion kilometers, 2.8 billion miles, from the Sun. This distance places it so far away that sunlight takes more than 4 hours to reach it, compared to just over 8 minutes for Earth. Because of its remoteness, Neptune is invisible to the naked eye, appearing only as a faint point through telescopes. Despite this, it is a massive world, the 4th largest planet by diameter and the 3rd largest by mass, making it a true giant of the outer solar system. Neptune's diameter is about 49,200 kilometers, 30,600 miles, roughly 4 times that of Earth. Its mass is about 17 times greater than Earth's, yet because of its enormous size, its average density is much lower. about 1.64 grams per cubic centimeter, compared to Earth's 5.51. This means Neptune is not a rocky world like Earth, but a so-called ice giant, composed mostly of lighter materials such as water, methane, and ammonia, along with a smaller amount of hydrogen and helium. Its density makes it slightly more compact than Uranus, which has a similar mass but a larger radius. One striking feature of Neptune is its deep blue appearance. This coloration comes primarily from methane gas in its upper atmosphere, which absorbs red wavelengths of sunlight while scattering blue ones. However, Neptune's color is richer and more vivid than Uranus's pale cyan tint, suggesting that other atmospheric components or processes contribute to its hue. This difference remains one of the mysteries of planetary atmospheres. Neptune has a day much shorter than Earth's. It rotates once on its axis in about 16 hours, giving it rapid spin rates that help shape its weather systems. Its axial tilt is about 28.3 degrees, close to Earth's 23.5 degrees. This tilt means Neptune experiences seasons, though they are extremely long due to its orbital period. A year on Neptune lasts about 165 Earth years, meaning each season spans over 40 years. Seasonal changes are subtle, but have been observed by telescopes as shifts in cloud patterns and brightness. In terms of gravity, Neptune is comparable to Earth. If you could stand on Neptune's cloud tops, which is impossible in reality as it has no solid surface, you would feel about 1.14 times Earth's gravity. This means a person weighing 70 kilograms, 154 pounds on Earth would weigh about 80 kilograms, 176 pounds on Neptune. Despite being a giant, its lower density balances its stronger mass, leading to surface gravity similar to ours. Neptune's orbit is another point of interest. It lies just beyond Uranus, with an average orbital distance of 30 astronomical units, AU, where 1 AU is the distance from Earth to the Sun. Its path around the Sun is almost perfectly circular, with an eccentricity of only 0.009. This regularity makes Neptune's orbit remarkably stable, unlike Pluto's, which is far more elongated. However, Pluto and Neptune share an unusual gravitational relationship. Pluto's orbit crosses inside Neptune's, but the two bodies are in a resonance that ensures they never collide. This resonance, called a 3-to-2 orbital resonance, is one of the many gravitational interactions that highlight Neptune's role in shaping the outer solar system. The temperature on Neptune is extreme. Its average cloud top temperature is about minus 214 degrees Celsius, minus 353 degrees Fahrenheit, making it one of the coldest places in the solar system. Yet paradoxically, Neptune radiates more than twice the heat it receives from the Sun. This internal heat source, still not fully understood, powers its dynamic atmosphere and contributes to the planet's turbulent weather systems. Despite its remoteness, Neptune exerts a significant influence over its surroundings. Its strong gravity shepherds moons and rings, and its magnetic field interacts with the solar wind in complex ways. It is a planet of contradictions, frigid yet active, distant yet influential, familiar in its gaseous makeup, yet unique in its features. In many ways, Neptune represents the frontier of planetary science. Its sheer distance makes it difficult to study, but its physical characteristics reveal it to be an essential piece of the solar system puzzle, bridging the gap between gas giants like Jupiter and Saturn and smaller rocky planets like Earth. Each basic fact about Neptune, its size, orbit, tilt, and color, hints at deeper mysteries that astronomers are still working to solve. The first impression Neptune makes, even through a telescope, is its extraordinary blue tone. Unlike the reddish hues of Mars or the golden shades of Saturn, Neptune's color is a deep, vibrant azure that immediately distinguishes it from other planets. This signature appearance is not just an aesthetic detail, but the result of complex atmospheric processes that give scientists clues about the planet's composition and dynamics. At its outermost layer, Neptune's atmosphere is primarily composed of hydrogen, about 80%, and helium, about 19%, with a small but crucial fraction of methane, roughly 1.5 to 2% of the upper atmosphere. Though small in quantity, methane plays an outsized role in shaping Neptune's color. Methane strongly absorbs red light from sunlight while reflecting blue and green wavelengths, which makes the planet look blue to our eyes. Uranus also contains methane in its atmosphere and shares a blue-green tint, yet Neptune's hue is noticeably darker and richer, suggesting that something more than methane absorption is at play. Astronomers believe additional atmospheric components or cloud structures contribute to Neptune's color. One hypothesis is that Neptune's atmosphere contains an as-yet unidentified haze, or particles that enhance the deep blue tones. Recent models propose that variations in aerosols and cloud thickness between Uranus and Neptune might explain the difference. Where Uranus has a thicker, haze-filled upper atmosphere that mutes its color into pale sheen, Neptune's atmosphere may be more transparent at certain layers, allowing its deeper, richer blues to shine through. Beyond color, Neptune's atmosphere is a laboratory of extreme weather. The upper atmosphere consists of distinct cloud layers, primarily made of methane ice crystals at higher altitudes and deeper clouds of ammonia, hydrogen sulfide, and possibly water ice. These clouds often form bright reflective patches that stand out against the darker blue background. Observations have shown that these clouds are dynamic, shifting rapidly and forming complex weather patterns. Some clouds resemble Earth's cirrus clouds, but on a vastly larger scale, spanning thousands of kilometers. The temperatures in Neptune's upper atmosphere are among the coldest in the solar system, averaging negative 214 degrees Celsius, negative 353 degrees Fahrenheit. However, paradoxically, Neptune has a significant internal heat source, radiating more than twice as much energy as it receives from the sun. This internal heat drives convection in its atmosphere, powering storms, winds, and large-scale circulation patterns. It also plays a role in maintaining Neptune's distinct cloud systems, fueling updrafts that loft methane ice into high altitudes. One of the most remarkable aspects of Neptune's atmosphere is the speed of its winds. These winds can reach up to 2,100 kilometers per hour, about 1,300 miles per hour, the fastest recorded in the solar system. At such speeds, clouds and storms whip around the planet in a matter of hours. For comparison, the strongest hurricanes on Earth top out at about 250 kilometers per hour, 155 miles per hour. The exact mechanism behind such supersonic winds is still debated, but scientists believe the combination of Neptune's rapid rotation, internal heat, and unique atmospheric composition creates conditions for these extremes. The upper atmosphere also reveals seasonal and long-term changes. With its 28-degree axial tilt, Neptune experiences seasons similar to Earth's, but each season lasts over 40 years due to its long orbital period. Subtle changes in atmospheric brightness have been observed over decades, possibly linked to seasonal shifts in solar energy or changes in cloud activity. Because we have only been able to observe Neptune for less than one of its years since its discovery, our perspective on its seasonal cycles is still very limited. Neptune's atmosphere remains one of its defining mysteries. While telescopes and spacecraft have provided tantalizing glimpses, the fine details of its chemistry, cloud layers, and dynamic processes are still poorly understood. The differences between Uranus and Neptune, despite their similarities in size and mass, underscore how small variations in atmospheric composition and internal energy can produce dramatically different appearances and behaviors. The striking blue color of Neptune, then, is more than a visual quirk. It is a window into the physics and chemistry of a distant world, reminding us that the beauty of the cosmos often reflects deeper truths waiting to be uncovered. Methane, though a minor component of Neptune's atmosphere, is one of the most influential substances shaping the planet's identity. Present at levels of about 1.5 to 2% in the upper atmosphere, methane is largely responsible for Neptune's deep blue color. Its molecular structure absorbs red light from the sun while allowing shorter wavelengths like blue and green to pass through and scatter back into space. Without methane, Neptune would look drastically different, likely appearing pale or whitish, similar to Jupiter and Saturn. Yet methane does more than just tint Neptune's appearance. It participates in a series of complex chemical reactions driven by sunlight and the planet's internal processes. When ultraviolet radiation from the sun strikes methane molecules, it breaks them apart in a process called photodissociation. This initiates chains of reactions that lead to the formation of hydrocarbons such as ethane, acetylene, and other organic compounds. These substances can clump together to form hazes and aerosols in the upper atmosphere. The hazes, produced by methane chemistry, play a major role in shaping Neptune's visible appearance and potentially in regulating its climate. These fine particles scatter sunlight and influence how heat is absorbed and radiated back into space. While Uranus also has a methane-rich atmosphere, its upper haze layer appears thicker, muting the planet's blue-green color. Neptune's thinner haze, on the other hand, lets deeper layers show through, giving the planet its darker, richer blue. Scientists are still studying why the two worlds differ so dramatically in haze thickness, despite having similar methane content. At deeper levels, methane contributes to the formation of clouds. Under the frigid conditions of Neptune's upper atmosphere, methane can condense into ice crystals, producing bright white or bluish clouds that drift across the planet. Observations from telescopes have revealed methane ice clouds forming and dissipating rapidly, suggesting that convection and vertical mixing constantly reshuffle the atmosphere. These processes may connect Neptune's cloud layers with its powerful winds and heat circulation, hinting at a tightly linked system of chemistry and dynamics. In addition to methane, Neptune's atmosphere contains other compounds in trace amounts. Hydrogen sulfide has been detected, particularly in deeper cloud decks, where it likely mixes with ammonia to form clouds. Hydrogen sulfide would smell like rotten eggs to a human observer, though the atmospheric pressures and temperatures on Neptune make it far more hazardous than just unpleasant. Scientists believe that the balance of hydrogen sulfide, ammonia, methane, and water ices in Neptune's interior influences both its weather systems and its long-term atmospheric stability. Another fascinating area of study is the possibility of diamond formation. Under immense pressures in Neptune's interior, methane may break down, with carbon atoms bonding together to form crystalline structures. Laboratory experiments simulating the high-pressure conditions of ice giants have shown that diamonds could indeed form in such environments. If this process occurs inside Neptune, it could mean that diamond rain falls deep into the planet's mantle, a phenomenon that is as scientifically significant as it is imaginative. Such a process would affect how heat is transported within the planet and could even influence its magnetic and gravitational properties. The chemistry of Neptune's atmosphere is not static. Changes in sunlight exposure, storm activity, and internal heat flux can all alter the balance of methane and its byproducts over time. Observations from the Hubble Space Telescope and ground-based observatories have shown seasonal and short-term variations in Neptune's brightness and cloud patterns, likely linked to shifts in atmospheric chemistry and dynamics. This variability makes Neptune's atmosphere one of the most dynamic among the outer planets. In short, methane is far more than a coloring agent. It is a central driver of Neptune's atmospheric processes, from the planet's visible clouds to its invisible chemical cycles. By studying methane and its reactions, scientists not only unravel the mysteries of Neptune, but also gain insight into atmospheric chemistry across the universe, since methane is a common molecule in many planetary environments. Neptune's weather systems are among the most violent and energetic in the solar system, a surprising fact given the planet's extreme distance from the sun. With less than 0.5% of the sunlight that Earth receives, Neptune would seem like a cold, quiet world. Instead, It hosts storms the size of continents, jet streams that circle the planet at supersonic speeds, and dynamic clouds that appear and disappear in a matter of days. The most famous of these storms is the Great Dark Spot, discovered by the Voyager 2 spacecraft during its 1989 flyby. Roughly the size of Earth, the storm resembled Jupiter's Great Red Spot, but with key differences. Unlike Jupiter's storm, which has persisted for centuries, Neptune's dark spots appear to be transient. The original Great Dark Spot observed by Voyager 2 vanished within a few years, replaced by other dark storms that appeared in different latitudes. Observations with the Hubble Space Telescope have shown that new storms can form, drift across the planet, and eventually dissipate, sometimes within just a decade. This constant cycle highlights Neptune's restless and unstable atmosphere. The winds that drive these storms are the fastest recorded anywhere in the solar system. In some regions, winds reach up to 2,100 kilometers per hour, about 1,300 miles per hour, nearly twice the speed of sound at sea level on Earth. These winds blow in both eastward and westward directions, forming alternating jet streams that wrap around the planet. The contrast between different wind bands fuels turbulence, leading to the development of vortices, wave patterns, and cloud streaks that can be tracked from Earth. Cloud activity on Neptune is another striking feature of its weather. Bright white clouds, often composed of methane ice crystals, form above storm systems and along jet streams. These clouds can appear and vanish in just hours, suggesting vigorous vertical mixing within the atmosphere. High-resolution observations have even revealed delicate cirrus-like clouds that stretch across hundreds of kilometers. Such transient features give Neptune a dynamic, ever-changing appearance, unlike the relatively stable belts and zones of Jupiter. Despite being far from the Sun, Neptune's atmosphere seems to generate more energy than it receives. The planet emits roughly 2.6 times as much heat as it absorbs from sunlight, indicating a powerful internal heat source. This excess heat may drive convection, fueling the intense storms and fast winds. Unlike Uranus, which radiates little internal heat, Neptune's internal energy appears to play a critical role in sustaining its weather systems. Scientists still debate the exact mechanism, but it could involve residual heat from the planet's formation, slow contraction of its interior, or exotic processes such as diamond precipitation releasing gravitational energy. Seasons also play a role in Neptune's weather. Because the planet takes 165 years to orbit the Sun, each season lasts over 40 years. Observations across decades have revealed gradual changes in the brightness of Neptune's atmosphere, likely linked to seasonal shifts. Some regions have become darker or brighter over time, and cloud activity has shifted in latitude. While these trends are still being studied, they suggest that Neptune's long seasons have a measurable effect on its atmosphere, even if the details remain mysterious. The interaction between storms and jet streams on Neptune provides important insights for planetary science. The constant birth and death of storm systems demonstrate how a planet's atmosphere can remain in a state of dynamic equilibrium. Storms form when conditions are favorable, transport heat and energy across the atmosphere, and then fade, making way for new systems. By studying this cycle, scientists learn not only about Neptune, but also about atmospheric physics in general, with applications to exoplanets and even Earth's weather. Neptune's weather systems highlight the paradox of the outer planets. The farther they are from the Sun, the less energy they receive, yet some of them, like Neptune, produce some of the most extreme weather phenomena in the solar system. It is a reminder that a planet's climate is not dictated by solar energy alone, but also by internal processes and atmospheric dynamics that we are still striving to understand. One of the strangest and most intriguing features of Neptune is its magnetic field. Unlike Earth, where the magnetic poles roughly align with the planet's rotation axis, Neptune's field is tilted by about 47 degrees relative to its spin. Even more unusual, the center of the magnetic field is offset by nearly 55% of the planet's radius, meaning the magnetic dipole is not anchored at the planet's core. This unusual geometry gives Neptune one of the most distorted magnetic fields in the solar system. Scientists believe this irregularity is tied to Neptune's interior structure. Unlike Earth, where the magnetic field is generated in a molten iron core, Neptune's field likely arises from the motion of electrically conductive materials within its mantle. The mantle of Neptune is not a rocky solid, but rather a thick layer of water, ammonia, and methane under immense pressure and temperature. In these extreme conditions, these substances may form a state called ionic water or superionic ice, where hydrogen and oxygen ions move freely, conducting electricity. The movement of this conductive fluid through convection and rotation creates a dynamo effect that generates the magnetic field. The offset and tilt may reflect the fact that this dynamo operates in a shell-like region rather than deep at the core. The result is a magnetic field that behaves very differently from Earth's. Charged particles trapped in Neptune's magnetosphere follow erratic paths, and the magnetosphere itself wobbles as the planet rotates. Voyager 2's flyby in 1989 provided direct measurements of this complex field, showing that the magnetosphere is asymmetric and varies dramatically in shape and orientation over time. In some cases, the solar wind can directly connect with Neptune's atmosphere due to this distortion, creating auroras that are far more scattered and uneven than the structured ovals we see on Earth. These auroras, caused by charged particles colliding with atmospheric molecules, are faint but significant. Unlike Jupiter's powerful auroras, which are fueled by interactions with its moon Io, Neptune's are weaker and more irregular, reflecting the chaotic geometry of its magnetic field. Still, their presence confirms that Neptune's magnetosphere actively interacts with the solar wind, despite the planet's distant location. The magnetosphere also acts as a protective shield, deflecting harmful solar and cosmic radiation. However, because of its odd shape and tilt, the level of protection varies across different regions of the planet. Some areas may be more exposed to charged particle bombardment, while others remain well shielded. This uneven distribution could influence Neptune's upper atmosphere, possibly playing a role in the patterns of haze and chemistry observed at high altitudes. Understanding Neptune's magnetic field is not just about one planet. It provides a valuable comparison point for Uranus, which also has a tilted and offset magnetic field. The similarities suggest that both ice giants generate their fields in comparable ways, distinct from the processes operating in gas giants like Jupiter and Saturn. These insights extend beyond our solar system, as many exoplanets likely share structural similarities with Neptune and Uranus. By studying how their magnetic fields arise, we can better understand the magnetic environments of countless distant worlds. The unusual magnetism of Neptune remains one of its great mysteries. The data from Voyager 2 offered a snapshot, but a dedicated orbital mission could reveal how the field changes over time, how it connects to the planet's interior, and how it interacts with the atmosphere. Until such a mission is flown, Neptune's magnetic personality will remain partly hidden, an enigmatic feature of an already puzzling planet. When people think of planetary rings, Saturn immediately comes to mind, with its vast, bright bands that dominate the night sky through a telescope. Yet Neptune also has a ring system, one that is subtle, dark, and easily overlooked. It was not until the late 20th century that astronomers confirmed their existence, and even today, Neptune's rings remain among the most mysterious structures in the solar system. The first hints of Neptune's rings came in the early 1980s, when astronomers observed stars briefly dimming as they passed behind the planet. These stellar occultations suggested that partial arcs of material encircled Neptune, but at the time it was unclear whether these were complete rings or just isolated clumps. It was Voyager 2's 1989 flyby that resolved the question. The spacecraft captured direct images of several faint rings encircling Neptune, confirming that the arcs were parts of continuous structures. Neptune's ring system is faint because it is composed of dark radiation-processed material. Unlike Saturn's icy rings, which reflect sunlight brightly, Neptune's rings are made mostly of small dust particles mixed with darker organic compounds. This makes them nearly invisible from Earth without specialized instruments. The rings are also narrow and uneven, with some showing striking clumps and arcs rather than smooth distributions of material. There are 5 main rings, named Gale, Leverrier, Lassell, Arago, and Adams, after astronomers connected with the discovery and study of Neptune. The outermost, the Adams ring, is the most famous because of its distinct arcs, which appear as bright segments within the otherwise faint structure. These arcs, with names such as Liberté, Égalité, and Fraternité, are unusual because, according to orbital mechanics, material in a ring should spread out evenly over time. Their persistence suggests that gravitational interactions with Neptune's moons, particularly Galatea, help maintain and confine them. This moon, orbiting just inside the Adams ring, acts as a shepherd shaping the ring's structure and preventing the arcs from dissipating. The rings are thought to be relatively young and short-lived on cosmic timescales. Micrometeoroid impacts and radiation from the sun gradually grind down and darken ring particles, suggesting that Neptune's rings may need to be replenished over time. Possible sources include impacts on nearby moons or fragments left over from past collisions. The uneven nature of the rings supports the idea that they are not ancient relics, but active, evolving structures shaped by ongoing processes. Neptune's rings also offer insight into the planet's history. They could be remnants of larger moons or icy bodies that broke apart due to collisions or tidal forces. Studying their composition and distribution provides clues about how Neptune's system has evolved and how moons and rings interact in dynamic environments. Though faint, Neptune's rings remain a crucial piece of the puzzle in understanding the ice giant. They demonstrate that ring systems are not unique to Saturn, but are instead a common outcome of planetary evolution, each with its own distinct character. For Neptune, the clumpy, dark rings reflect both its chaotic environment and the influence of its moons, revealing a world where even the smallest features carry deep stories about the solar system's past. Neptune has a fascinating collection of moons, each contributing a piece to the story of this distant planet. As of today, astronomers have confirmed at least 14 natural satellites orbiting Neptune, ranging from large and geologically active worlds to tiny irregular fragments, likely captured from the Kuiper Belt. Together, they form a miniature system of remarkable diversity. The most famous of Neptune's moons is Triton, discovered just 17 days after Neptune itself in 1846 by British astronomer William Lassell. Triton is unique in several ways. It is the only large moon in the solar system that orbits its planet in a retrograde direction, meaning it moves opposite to Neptune's rotation. This strongly suggests that Triton was not formed alongside Neptune, but was instead captured from the Kuiper Belt. Its capture would have been a violent process, likely destabilizing other moons and reshaping Neptune's satellite system into what we see today. Triton is roughly 2,700 kilometers, 1,680 miles, in diameter, making it larger than Pluto and one of the most geologically interesting bodies in the solar system. Voyager 2 revealed a surface shaped by cryovolcanism, geysers of nitrogen gas erupting from beneath the ice, and terrain marked by tectonic features. Its surface shows relatively few impact craters, indicating it is geologically young and active. This activity may be driven by internal heat, generated by tidal forces, as Triton's unusual orbit continues to stress and flex its interior. One of the most intriguing aspects of Triton is its thin atmosphere, composed mostly of nitrogen with traces of methane. Though tenuous, it supports weather patterns, including clouds and hazes that interact with surface activity. The presence of geysers observed by Voyager 2 indicates that sunlight warms dark patches on Triton's icy surface, causing subsurface nitrogen to vaporize and erupt. This dynamic interaction between surface, atmosphere, and interior makes Triton one of the most Earth-like ice worlds, despite being frigid and distant. Beyond Triton, Neptune's moons fall into two broad categories: inner regular moons and outer irregular moons. The inner moons, including Naiad, Thalassa, Despina, Galatea, Larissa, and Proteus, orbit close to the planet and likely formed from debris left after Triton's capture disrupted Neptune's original system. These moons are small, irregularly shaped, and heavily cratered, showing little evidence of geological activity. Proteus, the largest of the inner group, is about 420 kilometers, 260 miles, across and has a blocky, angular shape, suggesting it never had enough gravity to form into a sphere. Galatea is particularly important because of its role in shepherding Neptune's Adam's ring. Its gravity helps maintain the arcs within the ring, preventing them from spreading evenly around the planet. This moon-ring interaction highlights how even small bodies can exert significant influence in shaping planetary systems. The outer irregular moons, including Nereid and several smaller satellites discovered more recently, have wide, eccentric, and inclined orbits. Nereid, discovered in 1949, has one of the most eccentric orbits of any moon, ranging from 1.4 million kilometers, 870,000 miles, to over 9.6 million kilometers, 870,000 kilometers, 6 million miles from Neptune. Such an orbit points to a history of gravitational disturbances, likely tied to Triton's capture. The smaller irregular moons are believed to be captured Kuiper Belt objects, similar to Triton but on a much smaller scale. Together, Neptune's moons illustrate a complex history of capture, disruption, and reformation. Triton dominates the system, both in size and influence, but the smaller moons and rings show the aftermath of cosmic events billions of years ago. Studying these satellites not only deepens our understanding of Neptune, but also sheds light on how giant planets interact with surrounding populations of small bodies in the outer solar system. Triton is not only the largest moon of Neptune, but also one of the most remarkable and puzzling objects in the solar system. Its orbit, geology, and activity make it a world that defies expectations and demands special attention. One of Triton's most unusual features is its retrograde orbit. Unlike most large moons, which orbit in the same direction as their planet's rotation, Triton moves in the opposite direction. This retrograde motion is strong evidence that Triton was captured rather than formed in place. The most likely scenario is that Triton was once a Kuiper Belt object, similar to Pluto, and was pulled into Neptune's gravitational influence long ago. The capture event would have been catastrophic, destabilizing any pre-existing moons and possibly destroying them. The debris from that disruption may have contributed to the formation of Neptune's current smaller inner moons and faint rings. Triton's surface is a geologic laboratory of ice and activity. Voyager 2's 1989 flyby revealed a world that was far from static. Vast plains, ridges, valleys, and smooth surfaces suggest a history of tectonic reshaping. Large parts of the surface are strikingly young, showing few craters, which means Triton has been geologically active in recent times. Some regions are marked by cantaloupe terrain, a strange dimpled pattern not seen elsewhere in the solar system. The exact process that created it is still debated, but it highlights Triton's uniqueness. Cryovolcanism appears to play a major role on Triton. Instead of erupting molten rock like Earth's volcanoes, Triton's volcanoes spew water, ammonia, and other volatiles in the form of slurries or ices. Voyager 2 observed evidence of volcanic features and flows, suggesting that subsurface liquids or slushy mixtures have erupted onto the surface. This makes Triton one of the few places in the solar system where active cryovolcanism has been identified. Another dramatic discovery by Voyager 2 was Triton's geysers. These geysers, powered by sunlight heating the icy surface, erupt nitrogen gas mixed with dust into the atmosphere, creating plumes that rise several kilometers before drifting downwind. The geysers demonstrate that Triton's surface and atmosphere are linked in a dynamic system. Such activity was surprising, given Triton's great distance from the Sun, but it shows how even faint solar energy can drive processes when combined with volatile ices. Triton's thin atmosphere, composed mostly of nitrogen with traces of methane, adds to its complexity. Though tenuous compared to Earth's, it undergoes seasonal changes as Triton orbits Neptune. The atmosphere interacts with surface ices, causing them to freeze, sublimate, and redistribute over time. This cycle resembles Earth's hydrological cycle, but with nitrogen instead of water. The presence of methane in the atmosphere may also contribute to hazes, adding further complexity to the Moon's climate. From an orbital perspective, Triton is doomed. Because it orbits in the opposite direction of Neptune's rotation, tidal forces are gradually pulling it inward. Over billions of years, Triton will either crash into Neptune or be torn apart by gravitational forces, potentially forming a spectacular ring system much larger than Neptune's current faint rings. While this event is far in the future, it underscores the dynamic, evolving nature of planetary systems. The study of Triton has profound implications for planetary science. As a captured Kuiper Belt object, Triton provides a nearby example of the kinds of icy worlds that populate the outer solar system. Its active surface, cryovolcanism, and atmosphere make it a natural laboratory for understanding how such bodies evolve. In many ways, Triton serves as a bridge between planets and smaller icy bodies, offering insights into both categories. Future exploration of Triton is a high priority for planetary scientists. Missions have been proposed to orbit Neptune and study Triton in detail, with the potential to observe its geysers, map its surface with modern instruments, and probe its interior for signs of a subsurface ocean. If such an ocean exists, Triton could even be a candidate for habitability, albeit in a very different form than Earth. Its combination of activity, complexity, and uniqueness ensures that Triton will remain a key target for exploration in the decades to come. While Triton dominates Neptune's satellite system, the smaller moons provide crucial context for understanding the planet's history. They may not be as visually dramatic or geologically active, but their orbits, shapes, and roles within the system paint a picture of a planet shaped by disruption and capture. Closest to the planet are the inner moons, which orbit within just tens of thousands of kilometers from Neptune's cloud tops. These include Naiad, Thalassa, Despina, Galatea, Larissa, and Proteus. They are irregularly shaped, heavily cratered, and small, ranging from just a few tens of kilometers across to about 420 kilometers, 260 miles, in the case of Proteus. Their battered appearances and lack of geological features suggest they are ancient remnants, shaped by collisions and perhaps by the violent events surrounding Triton's capture. Naiad and Thalassa are especially interesting because of their orbital relationship. Naiad orbits slightly closer to Neptune than Thalassa, but the two never collide thanks to a synchronized orbital dance. For every 73 orbits of Naiad, Thalassa completes 69. This resonance keeps them out of each other's way, demonstrating the delicate gravitational balances that can stabilize even tiny moons. Such interactions reveal how small satellites can adapt to survive in crowded, dynamic environments. Galatea plays a central role in shaping Neptune's ring system. Orbiting just inside the Adam's ring, its gravity acts as a shepherd, confining the bright arcs that distinguish the ring. Without Galatea's influence, the arcs would likely disperse into a uniform band. This moon-ring interaction highlights how moons and rings evolve together, each influencing the other in subtle but powerful ways. Larissa, another inner moon, was first observed in 1981 during a stellar occultation, but its existence was only confirmed by Voyager 2 years later. Heavily cratered and irregular in shape, Larissa shows no signs of geological activity. Like the other inner moons, it is probably a survivor of ancient collisions, a fragment of a once larger body that was shattered. Proteus, the largest of Neptune's inner moons, stands out due to its size and appearance. At about 420 kilometers across, it is close to the size limit where gravity would normally pull a body into a spherical shape. Instead, Proteus remains blocky and irregular, with steep ridges and large craters. Its angular form suggests it never quite reached hydrostatic equilibrium, a state where gravity smooths a moon into a sphere. Proteus is likely one of the youngest of Neptune's larger moons, formed after Triton's capture disrupted the original system and produced debris that coalesced into new satellites. Farther out are Neptune's irregular moons, a group that includes Nereid and a collection of much smaller bodies discovered in recent decades. Nereid, found in 1949, is especially notable for its highly eccentric orbit, which swings it from 1.4 million kilometers, 870,000 miles, at closest approach to over 9.6 million kilometers, 6 million miles, at its farthest. This extreme orbit suggests it was perturbed by Triton's arrival, perhaps once being part of a larger, more stable group of moons that were scattered in the process. The smaller, irregular moons, many just tens of kilometers wide, orbit far from Neptune on elongated and tilted paths. These are believed to be captured Kuiper Belt objects, drawn into Neptune's gravitational pull long after the planet formed. Their presence demonstrates how Neptune interacts with its wider cosmic environment, sweeping up small bodies as it moves through the outer solar system. Together, Neptune's smaller moons show how violent and dynamic the planet's history has been. From shepherding rings to orbital dances to eccentric captures, each moon adds to the evidence that Neptune's system was reshaped dramatically when Triton was captured. They may be modest in size, but they are vital to the story of how a giant planet and its companions evolve over billions of years. Neptune is not just an isolated world on the edge of the Sun's domain. It plays a vital role in the broader architecture of the solar system, influencing the distribution of small bodies, shaping the Kuiper Belt, and even helping to define the boundary between the familiar inner system and the vast unknown beyond. Its gravitational presence has acted as a sculptor over billions of years, leaving imprints that extend far beyond its immediate neighborhood. One of Neptune's most important roles is its influence on the Kuiper Belt, the vast ring of icy bodies that lies just beyond its orbit. The Kuiper Belt is home to countless small objects, as well as dwarf planets such as Pluto, Haumea, and Makemake. Neptune's gravity has helped shape this region, clearing some areas, trapping objects in resonances, and scattering others into more distant orbits. For example, Pluto is in a 3-to-2 resonance with Neptune, meaning it completes 2 orbits of the Sun for every 3 Neptune completes. This orbital relationship ensures that Pluto never collides with Neptune, even though their paths cross. Many other Kuiper Belt objects occupy similar resonances, forming distinct populations that would not exist without Neptune's steady gravitational pull. Neptune also influences the scattered disk, a population of icy bodies with highly eccentric orbits that stretch far from the Sun. Many of these objects were likely thrown into their current paths by close encounters with Neptune early in the solar system's history. Some of them travel so far out that they blur the line between the Kuiper Belt and the more distant Oort cloud. By studying these populations, scientists can trace Neptune's role in redistributing material across the outer solar system. Beyond its gravitational influence, Neptune also serves as a boundary marker. It is the most distant of the 8 recognized planets, orbiting at an average distance of 4.5 billion kilometers, 2.8 billion miles, from the Sun. While dwarf planets and smaller bodies extend farther, Neptune is the last of the major worlds that anchor the solar system. Its orbit defines the edge of the planetary zone, beyond which lie the icy remnants of formation that never coalesced into planets. Neptune's placement has also shaped human exploration. Until its discovery in 1846, Uranus was thought to be the final planet. Neptune's existence, predicted mathematically before being observed, expanded our view of the solar system and hinted that its structure is more complex than once believed. The discovery also underscored the idea that gravity governs not just local interactions, but the layout of the solar system as a whole. In addition, Neptune plays a role in shaping comets. Many short-period comets, which orbit the Sun in less than 200 years, are believed to originate from the Kuiper Belt and were guided into their current paths by Neptune's gravitational nudges. The planet acts as a gatekeeper, sending some icy bodies inward while ejecting others entirely from the solar system. Its role in comet dynamics connects it to Earth, since comets have delivered both water and organic materials to our planet over time. Neptune's place in the solar system also has implications for exoplanetary science. Many exoplanetary systems contain Neptune-sized planets, often in closer orbits than our Neptune. By studying our own, scientists can compare its properties and behavior to these distant worlds. In a sense, Neptune serves as a local example of a very common type of planet in the galaxy, helping us bridge the gap between our solar system and the countless planetary systems beyond. In short, Neptune is more than just a cold, distant giant. It is a planetary architect, a gravitational shepherd, and a marker of the solar system's structure. Its influence stretches across billions of kilometers, shaping populations of icy bodies, stabilizing resonances, and directing the flow of comets. Understanding Neptune means understanding not just a single planet, but the outer solar system as a whole. Neptune's discovery is one of the most remarkable stories in the history of astronomy, because it was not first seen through a telescope, but predicted on paper. Its existence was revealed by mathematics before human eyes ever confirmed it. The story begins with Uranus, which had been discovered by William Herschel in 1781. Over the decades that followed, astronomers tracked Uranus's orbit with increasing precision. They noticed something odd. Uranus did not move exactly as Newton's laws predicted. Its path showed small but persistent deviations, as though another unseen body was tugging at it. These irregularities puzzled astronomers and hinted that another planet might lie farther out. Two mathematicians took up the challenge of solving this mystery independently: Urbain Le Verrier in France and John Couch Adams in England. Both calculated the probable position of a new planet that could account for Uranus's orbital disturbances. Their work showed extraordinary faith in Newtonian mechanics, applying mathematical reasoning to predict the existence of a world no one had yet observed. On September 23, 1846, German astronomer Johann Galle, using Le Verrier's calculations, pointed a telescope at the Berlin Observatory and found Neptune within 1 degree of the predicted position. The discovery stunned the scientific community. For the first time in history, a planet had been discovered through prediction rather than chance observation. It was a triumph of mathematics and a testament to the predictive power of Newton's laws. The discovery, however, was not without controversy. Adams had made his predictions earlier, but delays and lack of communication in England meant he did not receive credit at first. This sparked a dispute between French and British astronomers over who truly deserved recognition. In the end, history has acknowledged both Le Verrier and Adams as co-discoverers, though Galle was the one who first laid eyes on the planet itself. Early observations of Neptune revealed little detail. Through 19th century telescopes, it appeared as a faint bluish disk, far too small and distant to show surface features. Its mass, size, and orbital characteristics were gradually determined, but much of Neptune remained a mystery. Even the existence of its largest moon, Triton, was discovered almost immediately after the planet itself, in October 1846, thanks to William Lassell's careful observations. For decades, Neptune remained largely an enigma. Its faintness made it difficult to study, and unlike Jupiter or Saturn, it had no obvious features to track. Still, astronomers persisted, measuring its orbit, studying its faint light, and gradually building a picture of this distant world. The discovery itself also had philosophical implications, demonstrating that unseen forces could reveal hidden worlds and that the solar system might be more complex than previously imagined. In a way, Neptune's discovery also reshaped the practice of astronomy. It demonstrated the power of theoretical prediction and inspired confidence in using physics to guide observational work. This approach has since become standard in astronomy, applied not only to planets, but also to galaxies, dark matter, and even black holes. Neptune was the first major success of this predictive method, making it a turning point in the history of science. By the late 19th and early 20th centuries, Neptune became a fixture in astronomical charts, its orbit gradually refined, and its status as the 8th planet secure. Though much about its atmosphere, interior, and rings remained unknown, its presence in the solar system was undeniable, a distant but real world discovered not by chance, but by reason. For much of human history, Neptune remained little more than a faint blue dot in telescopes, its secrets hidden by distance. That changed dramatically in 1989, when Voyager 2 became the first and so far the only spacecraft to visit Neptune. The encounter transformed our understanding of the planet, turning abstract theories into vivid, tangible discoveries. Voyager 2 was launched in 1977 as part of NASA's ambitious plan to take advantage of a rare alignment of the outer planets. The spacecraft visited Jupiter in 1979, Saturn in 1981, and Uranus in 1986 before reaching Neptune on August 25, 1989. The journey to Neptune took more than a decade, but the wait was worth it. In just a few days of close flyby, Voyager 2 revealed more about Neptune than centuries of Earth-based observation had managed. As the spacecraft approached, scientists got their first clear views of Neptune's atmosphere. To their surprise, the planet was far from bland. Voyager 2's images revealed active weather systems, including massive storms and fast-moving clouds. The most striking feature was the Great Dark Spot, a storm system nearly the size of Earth. Accompanying it were bright white clouds of methane ice, nicknamed scooters for their rapid motion across the atmosphere. The discovery shattered assumptions that Neptune would be quiet and featureless, instead showing it to be a dynamic, turbulent world. The spacecraft also measured Neptune's winds and found them to be the fastest in the solar system, reaching speeds of 2,100 kilometers per hour, 1,300 miles per hour. This was astonishing given Neptune's great distance from the Sun, which provides little energy to drive such activity. The data confirmed that Neptune's internal heat plays a major role in powering its atmosphere. Voyager 2 also provided the first detailed look at Neptune's ring system. The faint rings, hinted at by earlier occultation studies, were imaged directly for the first time. The spacecraft confirmed the existence of clumpy arcs in the outer Adam's ring, as well as several fainter rings closer in. These observations raised new questions about how the rings remain stable and what processes sustain them. The flyby revealed Neptune's moons in unprecedented detail. Proteus, the largest inner moon, was seen up close for the first time, showing an irregular, heavily cratered surface. But the most spectacular discovery came from Triton. Voyager 2 revealed Triton to be a world unlike any other, geologically active, with nitrogen geysers erupting from its surface, and a landscape shaped by cryovolcanism and tectonics. Its young surface, strange cantaloupe terrain, and thin atmosphere transformed Triton from a distant speck into one of the most intriguing bodies in the solar system. In addition to visual discoveries, Voyager 2 measured Neptune's magnetic field. Like Uranus, it was found to be tilted and offset from the planet's center, creating a lopsided and dynamic magnetosphere. The data supported the idea that Neptune's field is generated in a shell of conductive fluids rather than a central core. The flyby lasted only a matter of hours as Voyager 2 sped past Neptune at over 90,000 kilometers per hour, 56,000 miles per hour, Yet its impact has lasted for decades. The spacecraft continued on toward interstellar space, but Neptune remained behind, forever changed in human understanding. Voyager 2's encounter with Neptune was the capstone of the grand tour of the outer planets, a sequence of missions made possible by the alignment of the giant planets in the late 20th century. It left behind a treasure trove of data that scientists are still analyzing today. With no new missions to Neptune currently scheduled, Voyager 2's flyby remains our only direct exploration of the ice giant, making it one of the most important events in the history of planetary science. After Voyager 2's historic flyby in 1989, Neptune once again became a distant world, beyond the reach of spacecraft. But astronomy didn't stop there. Instead, Earth-based observatories, and most importantly, the Hubble Space Telescope, continued the work of uncovering Neptune's secrets. Over the past 3 decades, Hubble and other advanced instruments have transformed our view of Neptune from a snapshot captured in the late 20th century into a living, changing world. Hubble's observations of Neptune began not long after its deployment in 1990. Although it orbits Earth, Hubble's position above the atmosphere gives it a clarity unmatched by ground-based telescopes. For Neptune, this advantage was critical. The planet's distance makes it appear tiny in Earth-based telescopes, but with Hubble's sharp eye, astronomers could monitor Neptune's atmosphere over time. What they found was that Neptune's weather is far from static. One of Hubble's most surprising contributions was the discovery of new dark storms. Voyager 2's Great Dark Spot had vanished by the time Hubble began regular observations, but the telescope soon spotted fresh storms forming in Neptune's atmosphere. These were massive anticyclones, similar in nature to the original storm but located in different latitudes and sizes. Some appeared and disappeared within a few years, suggesting Neptune's storms are more transient than the Great Red Spot on Jupiter, which has persisted for centuries. In 2018, Hubble recorded the formation of another large dark vortex in Neptune's northern hemisphere, one of several documented in recent decades. This discovery confirmed that Neptune's atmosphere is constantly reshaping itself, with storms that can both emerge suddenly and dissipate quickly. These storms are often accompanied by bright, fast-moving methane clouds that serve as visual markers of the turbulence beneath. Beyond weather, Hubble has helped astronomers refine Neptune's seasonal changes. A Neptune year lasts 165 Earth years, meaning each season spans more than 40 years. Hubble's long-term monitoring provides the only reliable way to detect subtle shifts in atmospheric brightness and cloud activity that may correspond to seasonal cycles, while a full seasonal change has yet to be observed. Hints of gradual transitions are becoming visible as the planet moves through its long orbit. Advances in adaptive optics on ground-based telescopes have also added to the picture. Observatories like Keck in Hawaii and the Very Large Telescope in Chile use laser-guided systems to correct for atmospheric distortion, bringing their clarity close to Hubble's. These instruments have captured stunning images of Neptune's storms and helped track the movement of its moons and faint rings. The James Webb Space Telescope, launched in 2021, has recently, though, added even more depth to Neptune research. With its infrared vision, Webb can peer through Neptune's upper haze and reveal structures invisible in visible light. Early images from Webb highlighted Neptune's rings with extraordinary clarity, as well as intricate atmospheric patterns and heat signatures from its interior. This new perspective complements decades of Hubble data, offering a multi-wavelength view of the ice giant. Together, Hubble, Webb, and powerful ground-based telescopes have kept Neptune alive in scientific study, long after Voyager 2's fleeting visit. Instead of being a frozen relic at the edge of the solar system, Neptune is now seen as a restless, evolving world, constantly reshaping itself in ways we are only beginning to understand. When Voyager 2 passed by Neptune in 1989, it not only captured the first close-up images of the planet itself, but also revealed the stunning complexity of its largest moon, Triton. This moon, which orbits Neptune in the opposite direction of the planet's rotation, immediately stood out as one of the most unusual bodies in the solar system. In the years since, scientists have continued to study Voyager's data, while also making new observations with Earth-based and space-based telescopes, trying to make sense of this strange world. One of the most important aspects of Triton is its retrograde orbit. Unlike Neptune's other moons, which orbit in the same direction that Neptune rotates, Triton moves in the opposite direction. This unusual pattern strongly suggests that Triton did not form alongside Neptune, but was instead captured from elsewhere. The most widely accepted theory is that Triton was once a Kuiper Belt object, similar to Pluto, that strayed too close to Neptune's gravity and was pulled into orbit. This event would have been catastrophic, potentially disrupting or ejecting Neptune's original moons before Triton settled into its current path. Voyager's images showed that Triton has a young ice surface, crisscrossed with ridges, plains, and strange cantaloupe terrain, unlike anything seen elsewhere. This appearance suggests that Triton has been geologically active in the relatively recent past. In fact, Voyager 2 recorded plumes erupting from the surface, evidence of active geysers spewing nitrogen gas into space. This was astonishing, as it made Triton the first icy moon beyond the giant planets to be observed with current geological activity. Since then, astronomers have continued to study Triton from afar. Hubble and other telescopes have tracked its orbit and surface changes, though the distance limits the detail that can be seen. Observations in infrared wavelengths suggest that Triton's surface is covered with a thin layer of frozen nitrogen, with traces of methane and carbon monoxide ices as well. Seasonal sunlight may heat these ices just enough to create pressure below the surface, leading to the geysers Voyager witnessed. The prospect of a subsurface ocean beneath Triton's crust has also become an exciting area of research. If such an ocean exists, it could be sustained by tidal heating from Neptune's gravity, much like the activity seen on Europa or Enceladus. This would make Triton a potential candidate for habitability, even though it lies at the edge of the solar system. The possibility that life could exist, or once existed, beneath its icy shell adds urgency to calls for a dedicated mission to return to Neptune and Triton. NASA has considered proposals such as the Trident mission, a concept for a flyby spacecraft that would revisit Triton, capture high-resolution images, and probe its potential ocean. While not yet funded, interest remains high because Triton combines the intrigue of an active surface, the mystery of its origin, and the potential for an oceanic interior. For now, Triton remains frozen in Voyager's snapshots, with only hints added by Earth-based and space telescope observations. Yet its story continues to capture the imagination of planetary scientists. Unlike many other moons, which fit neatly into their planet's formation story, Triton stands as a captured outsider, reshaped by Neptune's gravity, but still holding secrets of its earlier life. Every glimpse we have suggests that if a spacecraft were to return, it would uncover a world as dynamic and surprising as any in the solar system. Magnetic fields are among the most fascinating features of the giant planets, and Neptune's magnetosphere is no exception. When Voyager 2 flew past the planet in 1989, scientists expected something similar to Jupiter or Saturn, a powerful magnetic field aligned roughly with the planet's rotation. Instead, what they found was far stranger, and it forced planetary scientists to rethink how planetary dynamos might work deep inside ice giants. Neptune's magnetic field is tilted by about 47 degrees from its rotational axis, and its magnetic center is offset by more than 13,000 kilometers, around 8,000 miles, from the planet's physical center. This makes Neptune's magnetosphere lopsided and highly variable, As the planet rotates, the magnetosphere wobbles and sweeps around space in a complex pattern, creating a constantly shifting shield against the solar wind. For comparison, Earth's magnetic field is tilted by only about 11 degrees, and it is nearly centered, which makes it much more stable. The unusual shape of Neptune's magnetosphere suggests that its magnetic field is not generated deep in its metallic core, as with Earth, but instead arises from electrical currents in a shell of electrically conductive water-ammonia ocean located higher up within the planet. This shallower dynamo would produce a more distorted and unstable field, explaining both the tilt and the offset. Uranus, interestingly, has a very similar magnetic configuration, which hints that the ice giants share a different internal mechanism compared to the gas giants Jupiter and Saturn. Voyager 2 detected charged particles trapped in Neptune's magnetic field, forming radiation belts similar to those around Earth, Jupiter, and Saturn. However, Neptune's belts were weaker than Jupiter's, but still significant enough to pose hazards to spacecraft. The complex geometry of the magnetosphere also means that these belts shift and vary more than those of other planets. Understanding these radiation zones is essential for planning any future missions, as they influence how close a spacecraft could approach and how long it could survive in orbit. Neptune's interaction with the solar wind also creates dramatic auroras, though they differ from those on Earth or Jupiter. Instead of forming neat ovals around the magnetic poles, Neptune's auroras appear in scattered patches across the planet. This chaotic distribution reflects the irregular geometry of its field. Observations from the Hubble Space Telescope and other instruments have confirmed that Neptune does indeed host auroral activity, though it is much fainter than on other planets and more difficult to observe from Earth. Another interesting aspect is how Neptune's magnetic environment interacts with its moons and rings. Triton, in particular, orbits within Neptune's magnetosphere and may generate its own auroras due to charged particles striking its surface and atmosphere. The interactions between Neptune's tilted field and its satellites likely produce complex electromagnetic effects, though these remain poorly studied. Scientists hope that by studying Neptune's magnetosphere in more detail, they can refine models of how planetary dynamos work. Since ice giants may be more common than Jupiter-like gas giants in other solar systems, understanding Neptune's unusual field could also help interpret the magnetic environments of exoplanets. In this way, Neptune's lopsided magnetosphere is not just a curiosity. It may hold broader lessons about how planets generate and sustain magnetic shields across the universe. At nearly 30 times farther from the Sun than Earth, Neptune resides in a region where the solar wind is weaker and more diffuse, but it still plays an important role in shaping the planet's space environment. The solar wind, a continuous stream of charged particles, mostly protons and electrons, flowing outward from the Sun, creates interactions with every magnetic field it encounters. For Neptune, with its tilted and off-center magnetosphere, the result is a highly dynamic and unpredictable relationship. When the solar wind strikes Neptune's magnetic field, it compresses the magnetosphere on the side facing the Sun while stretching it into a long tail on the night side, much like at Earth. However, because Neptune's magnetic field is both tilted and offset, the boundaries of its magnetosphere shift and wobble dramatically as the planet rotates. This means the magnetopause, the outer boundary of the magnetosphere, constantly changes in size and orientation, sometimes expanding, sometimes contracting in ways far more extreme than at Earth or Jupiter. Voyager 2's flyby provided the first and only direct measurements of this interaction. Instruments detected variations in charged particles and magnetic field strength that pointed to a magnetosphere in flux. The data suggested that the solar wind can penetrate Neptune's protective bubble more easily than at planets with more stable fields. This allows bursts of solar particles to enter, energizing Neptune's magnetosphere and possibly fueling auroral events. The solar wind at Neptune's distance also carries less energy than it does at Earth, but it is not insignificant. Large solar storms can send powerful gusts outward that eventually reach Neptune after traveling through the solar system for several days. These events can cause dramatic compressions of Neptune's magnetosphere, triggering disturbances that ripple across its magnetic field and radiation belts. In fact, studying such distant interactions gives scientists a way to test how solar activity propagates through the heliosphere, the vast bubble of space influenced by the sun. Auroras at Neptune are one of the clearest signs of solar-wind interaction. Unlike Earth's northern and southern lights, which form neat ovals around the poles, Neptune's auroras appear irregular and scattered. This is again due to the planet's odd magnetic geometry. When charged particles from the solar wind funnel along Neptune's field lines, they strike the upper atmosphere and excite hydrogen atoms, producing faint glows of ultraviolet light. These auroras are far too faint for the human eye to see and can only be detected with sensitive instruments like the Hubble Space Telescope. Beyond Neptune, the solar wind continues outward until it meets the boundary of interstellar space. This makes Neptune the last planet within the Sun's direct influence that we can study up close. Its magnetosphere and solar wind interactions offer a natural laboratory for testing theories about how stellar winds behave in distant planetary systems. Since many exoplanets discovered so far orbit far from their stars, Neptune provides a valuable analogy for what those distant worlds might experience. Future missions to Neptune would undoubtedly dedicate instruments to measuring the solar wind and its interaction with the planet's magnetic field. Such studies would not only reveal more about Neptune itself, but also about how solar activity shapes the outer edges of the solar system. In the meantime, astronomers rely on telescopes and computer simulations to model these processes. But the Voyager 2 flyby remains the only source of direct data. The hope is that a new mission will one day return to this distant planet and capture the full dynamics of Neptune's dance with the solar wind. The discovery of the Kuiper Belt in the early 1990s transformed our understanding of the outer solar system, and Neptune plays a central role in its structure. The Kuiper Belt is a vast region beyond Neptune, filled with icy bodies, dwarf planets, and debris left over from the early solar system. Its objects orbit the Sun in a variety of paths, but many of those paths are directly influenced by Neptune's gravity. Without Neptune, the Kuiper Belt would look very different than it does today. One of Neptune's most important contributions is the creation of orbital resonances. These occur when a Kuiper Belt object, KBO, completes a set number of orbits around the Sun in the same time it takes Neptune to complete a different set. For example, Pluto is in a 3-to-2 resonance with Neptune, meaning that for every 3 orbits Pluto makes, Neptune completes 2. This resonance prevents close encounters and keeps Pluto's orbit stable, even though it crosses inside Neptune's orbital path. Many other KBOS are locked into similar resonances, showing how Neptune sculpts the population of the region. Neptune's migration in the early history of the solar system was another major factor. Models suggest that Neptune did not form where it currently resides, but instead migrated outward after the solar system's formation. As it moved, Neptune's gravity scattered countless icy planetesimals, some being ejected completely from the solar system, others being thrown inward, and many being trapped in resonances that still define their orbits today. This sweeping migration is thought to have shaped the architecture of the Kuiper Belt, explaining why objects are grouped into certain orbital families. The presence of scattered disk objects, KBOS, with highly elongated, tilted orbits, also points to Neptune's influence. These bodies were likely tossed into their current paths by close gravitational encounters with Neptune in the past. Even today, Neptune continues to shape the outer solar system, slowly tugging on objects over millions of years and altering their orbits. The Kuiper Belt is not just a collection of random icy rocks. It is a fossil record of the solar system's youth, and Neptune is one of the main reasons that record looks the way it does. By studying the orbital distribution of KBOS, scientists can backtrack Neptune's history and refine models of planetary migration. The discovery of numerous resonant populations, such as the Plutinos in the 3-2 resonance, provides compelling evidence for Neptune's outward journey billions of years ago. Understanding Neptune's role in the Kuiper Belt also has implications for exoplanetary systems. Many distant stars host belts of debris similar to our Kuiper Belt, and studying Neptune's influence gives astronomers a model for how giant planets can sculpt and control such structures elsewhere. Neptune, in this sense, is a key to unlocking the story not only of our own solar system, but also of planetary systems across the galaxy. For spacecraft missions, Neptune's position at the inner edge of the Kuiper Belt makes it a natural gateway. A mission to Neptune could also be designed to continue onward to study Kuiper Belt objects directly, much like New Horizons did after flying past Pluto. This dual purpose, exploring Neptune and the Kuiper Belt, strengthens the case for returning to the outer solar system with a new mission in the coming decades. The solar system may look calm and orderly from our perspective, but beneath the surface lies a delicate balance of gravitational forces. Neptune, as the most distant giant planet, plays a surprisingly important role in maintaining that balance. Its gravity not only affects the Kuiper Belt, but also influences the long-term stability of the solar system as a whole. One of Neptune's key functions is as a cosmic gatekeeper. Its gravity acts as a barrier between the inner solar system and the reservoir of icy bodies that orbit farther out. Without Neptune's stabilizing influence, many more Kuiper Belt objects and comets could wander into the inner solar system, potentially creating chaotic conditions for the terrestrial planets. In this way, Neptune reduces the frequency of disruptive encounters, helping to preserve the relatively stable environment Earth has enjoyed for billions of years. Neptune also shapes the orbits of the other giant planets through subtle gravitational interactions. Early in the solar system's history, the so-called NICE model suggests that Neptune's outward migration destabilized a vast population of icy planetesimals, sending many inward and outward. This event may have triggered what is known as the Late Heavy Bombardment, a period of intense impacts on the Moon and planets. Yet once Neptune reached its current orbit, its presence helped to stabilize the architecture of the giant planet system, locking it into the arrangement we see today. Computer simulations show that Neptune's position and mass are crucial for this balance. If Neptune were much larger or smaller, or if its orbit were slightly different, the entire outer solar system could evolve in dramatically different ways. For example, a more eccentric orbit might destabilize resonant Kuiper Belt populations, while a slightly closer orbit could disrupt Uranus or alter Saturn's long-term stability. The precise arrangement of the planets seems finely tuned, and Neptune is one of the cornerstones of that configuration. Another area where Neptune contributes to stability is in the regulation of comets. Long-period comets that come from the distant Oort cloud often pass through Neptune's domain on their way inward. Neptune's gravity deflects many of these comets, either ejecting them from the solar system entirely or altering their paths so they do not repeatedly threaten the inner planets. This shepherding role reduces the likelihood of catastrophic impacts on Earth and its neighbors, indirectly shaping the conditions for life. At the same time, Neptune's influence can sometimes introduce instability. Its gravitational nudges occasionally send objects into eccentric orbits that eventually bring them closer to the Sun. While rare on human timescales, over millions of years, these interactions help replenish the population of short-period comets we see today. This dual role, as both stabilizer and instigator, makes Neptune a key player in the ongoing dynamical evolution of the solar system. Looking ahead, studying Neptune's gravitational influence gives scientists valuable insights into planetary system dynamics beyond our own. Many exoplanetary systems discovered so far include giant planets in distant orbits, and Neptune provides a natural laboratory for understanding how such planets shape the stability of their systems. The balance Neptune helps maintain in our solar system may not be universal, and comparing it with other systems can reveal just how rare or common our configuration might be. In this sense, Neptune is more than just a distant, cold planet. It is one of the architects of the solar system's stability. Its presence has helped shape the environment that allowed life to emerge on Earth, and its continuing influence ensures that the solar system remains a relatively calm place in a universe often characterized by chaos. The origin of Neptune has long puzzled scientists. Unlike the gas giants Jupiter and Saturn, which are thought to have formed relatively quickly in the early solar system, Neptune and Uranus present unique challenges for models of planet formation. Their position in the solar system, their composition, and their relatively small masses compared to Jupiter and Saturn suggest that the processes that created them were more complicated than initially assumed. One of the major questions is how Neptune managed to form so far from the Sun. In the standard model of planet formation, known as the core accretion model, solid particles collide and stick together to form larger bodies, eventually creating a rocky core massive enough to attract gas from the surrounding protoplanetary disk. However, in the cold, distant regions of the solar system where Neptune resides, material is sparse, and the timescales for this process become very long. Some models suggest it would take longer than the age of the solar system for Neptune to grow to its current size in its present location. To solve this puzzle, many scientists believe Neptune did not form where it currently is. Instead, it likely formed closer to the Sun, in a region with more material, before migrating outward. The NICE model, developed in the early 2000s, provides one of the most compelling scenarios. In this model, the giant planets, Jupiter, Saturn, Uranus, and Neptune, were initially packed more closely together. Interactions with a massive disk of icy planetesimals beyond them caused Neptune and Uranus to move outward over time. During this migration, Neptune's gravity scattered countless smaller bodies, some of which were ejected entirely from the solar system, while others were captured into resonant orbits. This explains the structure of the Kuiper belt today, including the orbital resonance of Pluto and the presence of scattered disk objects. The outward movement of Neptune is also thought to have triggered the Late Heavy Bombardment, a period of intense impacts on the inner planets about 4 billion years ago, as displaced objects from the outer solar system rained inward. Another question concerns why Neptune and Uranus ended up with relatively small gas envelopes compared to Jupiter and Saturn. One possibility is that they formed later, when the gas in the protoplanetary disk was already dissipating, leaving them with only modest atmospheres. Alternatively, their growth may have been interrupted by the migration process, limiting how much gas they could accumulate. This difference in timing and environment may explain why Neptune is classified as an ice giant rather than a true gas giant. Recent computer simulations and improved observations of exoplanetary systems have provided additional insights. Many exoplanet systems include planets similar in size to Neptune, suggesting that planets of this type are common in the universe. This strengthens the idea that Neptune represents a successful mode of planet formation under certain conditions, rather than an anomaly. By comparing Neptune with exoplanets, scientists can refine models of how migration and core growth interact across a wide range of systems. The precise details of Neptune's migration are still debated. Some models suggest it may have switched positions with Uranus during the process, explaining why Uranus has a more extreme axial tilt. Others propose that Neptune's migration was not smooth, but rather punctuated by sudden jumps caused by gravitational encounters with other large bodies. These variations show that while the broad picture is becoming clearer, the fine details of Neptune's early history remain open questions. Ultimately, Neptune's formation and migration are central to understanding not just the outer solar system, but also planetary systems throughout the galaxy. By piecing together its history, scientists gain insights into the processes that shape planetary architectures, the frequency of ice giants, and the conditions that lead to stable, life-friendly systems like our own. When astronomers classify the planets of our solar system, they usually divide them into three main categories: terrestrial planets like Earth, gas giants like Jupiter and Saturn, and the ice giants Uranus and Neptune. The term ice giant may sound misleading at first. Neptune is not covered in frozen water like a comet. Instead, it refers to the fact that a significant portion of its mass is made of substances heavier than hydrogen and helium, often called ices in planetary science. These include water, ammonia, and methane, which exist under exotic forms in Neptune's deep interior. Compared to Jupiter and Saturn, Neptune is relatively small, with a mass 17 times that of Earth, while Jupiter is over 300 Earth masses. What distinguishes Neptune and Uranus is not just their size, but their composition. While gas giants are dominated by hydrogen and helium, ice giants contain only about 10 to 15% hydrogen and helium by mass. The rest is a mixture of heavier materials. This makes their interiors more complex, and their atmospheres more enriched with methane and other molecules that give them their striking blue color. The idea of ice giants as a distinct category only became clear in recent decades. For a long time, Uranus and Neptune were lumped together with Jupiter and Saturn simply as giant planets. But as scientists learned more about their densities, atmospheres, and magnetic fields, it became clear that Neptune and Uranus formed in different conditions and have different structures. They are not merely smaller versions of Jupiter, but represent a unique type of planet. This distinction has taken on new importance with the discovery of exoplanets. Surveys have found that Neptune-sized worlds are among the most common types of planets in our galaxy, even though our own solar system has only two. These so-called mini-Neptunes often orbit much closer to their stars than Neptune does to the Sun, creating hot, exotic versions of our ice giants. By studying Neptune in detail, astronomers hope to build a bridge between what we can see in our own solar system and the distant worlds detected around other stars. Neptune also serves as a useful comparison to Uranus. On the surface, the two planets seem like twins, with similar sizes, colors, and compositions. Yet they differ in some important ways. Neptune is slightly more massive, has stronger winds, and emits more internal heat. Uranus, in contrast, appears almost inert, with very little heat flow from its interior. These differences suggest that even among ice giants, there can be significant variety depending on their histories and internal processes. Neptune, therefore, helps highlight the diversity within this planetary class. The concept of ice giants has reshaped how scientists think about planetary formation. Theories now suggest that there may be a natural dividing line between planets that grow massive enough to become gas giants and those that stop at the ice giant stage. If Neptune had formed earlier or accreted just a bit more material, it might have captured a much larger envelope of hydrogen and helium, making it more like Saturn. Instead, it froze in place as an ice giant, giving us a valuable window into this intermediate type of planet. In summary, Neptune's place among the ice giants marks it as both a unique member of our solar system and a key representative of one of the most common planet types in the universe. Its study not only tells us about our own planetary neighborhood, but also provides crucial context for understanding the thousands of Neptune-like worlds discovered around other stars. For much of history, Saturn was thought to be the only planet with rings. That changed in the late 20th century, when faint ring systems were detected around Jupiter, Uranus, and Neptune. Among these, Neptune's rings stand out as both fragile and puzzling. They are not as bright or extensive as Saturn's, but their very existence provides valuable clues about the processes shaping the outer solar system. Neptune's rings were first suspected in the early 1980s, when astronomers observing stellar occultations noticed that starlight sometimes dimmed briefly before and after Neptune passed in front of it. These brief dips suggested that something thin and narrow, likely ring material, was blocking the light. However, the observations were inconsistent, with some dips missing, leading scientists to suspect that Neptune had arcs of material rather than complete rings. This mystery was finally solved in 1989, when Voyager 2 flew past Neptune and confirmed the presence of faint, dusty rings encircling the planet. Voyager's images showed that Neptune has 5 main rings, named Gale, Leverrier, Lassell, Arago, and Adams. They are narrow and dark, made mostly of dust and small ice particles coated with radiation-darkened material. Unlike Saturn's bright, icy rings, Neptune's are difficult to see and reflect little sunlight. The Adams ring, the outermost, is especially famous because it contains distinct arcs, clumps of material that seem to defy the natural spreading that would normally occur due to orbital mechanics. The persistence of these arcs remains one of the great mysteries of Neptune's rings. Under normal conditions, particles in a ring should spread out evenly over time, smoothing away any clumps. Yet the arcs in the Adams ring remain confined, suggesting that some stabilizing mechanism is at work. One leading theory is that Neptune's moon Galatea, which orbits just inside the Adams ring, exerts gravitational shepherding that helps maintain the arcs. This idea explains how the arcs are kept in place, but does not fully account for their precise distribution. The rings themselves are thought to be relatively young, perhaps only a few 100 million years old, and may be replenished by collisions among small moons or fragments. The dark material coating the ring particles could be the result of radiation from the solar wind and Neptune's magnetosphere, which gradually alters the icy surfaces into darker, carbon-rich compounds. This process likely makes the rings appear fainter over time compared to the bright, icy rings of Saturn. Studying Neptune's rings also offers broader insights into ring dynamics across the solar system. While Saturn shows what a massive, long-lived ring system can look like, Neptune demonstrates the other extreme, a faint, tenuous system shaped by interactions with nearby moons. Together, they show the diversity of ring systems and the delicate balance of forces that create and maintain them. Observations with the Hubble Space Telescope and, more recently, ground-based observatories equipped with adaptive optics have tracked Neptune's rings over the decades since Voyager. Intriguingly, some observations suggest that the arcs may be changing or fading, raising questions about their long-term stability. If true, this would mean that Neptune's rings are more dynamic and ephemeral than once thought. Future missions to Neptune would likely focus on these rings as one of their key targets. High-resolution imaging could reveal how the arcs are maintained, what they are made of, and whether new structures are forming or disappearing over time. Such data would not only solve a long-standing mystery about Neptune, but also refine our understanding of how ring systems evolve across the solar system. When astronomers began detecting exoplanets in the 1990s, they expected to find worlds similar to those in our solar system. Instead, the first discoveries were dominated by hot Jupiters, giant planets orbiting extremely close to their stars. Over time, however, surveys revealed that one of the most common types of exoplanets in the galaxy is the Neptune-sized planet. These worlds, often called mini-Neptunes or sub-Neptunes, bridge the gap between Earth-like rocky planets and massive gas giants, making Neptune in our solar system an essential reference point. Neptune provides a benchmark for understanding what these common exoplanets might be like. With a mass about 17 times that of Earth and a radius roughly 4 times larger, Neptune represents a middle ground between small terrestrial worlds and the gas giants Jupiter and Saturn. Its composition, dominated by water, ammonia, and methane ices, mixed with hydrogen and helium, offers a model for the internal structure of many exoplanets that fall into the same size and mass range. By studying Neptune in detail, scientists can refine models of these distant worlds, even if we cannot directly observe their surfaces or interiors. One of the key lessons from Neptune is the importance of atmospheric composition. Neptune's methane-rich atmosphere gives it a striking blue color and reveals how different chemical abundances affect the appearance of a planet. For exoplanets, detecting atmospheric gases is one of the main ways astronomers can characterize them. If a mini Neptune around another star shows methane, water vapor, or other molecules in its spectrum, comparisons with Neptune can help interpret what that means for its structure and environment. Neptune also highlights the diversity possible within the Neptune size category. Even though Uranus and Neptune are often lumped together, they differ in heat output, weather activity, and possibly internal layering. Exoplanets in this size range are likely to be even more diverse. Some may resemble Neptune closely, with thick hydrogen-rich atmospheres, while others may have thinner atmospheres or even stripped envelopes, leaving behind rocky cores. Neptune serves as a reminder that size alone does not determine a planet's nature. Its history, formation, and environment matter just as much. Another connection between Neptune and exoplanet studies lies in planetary migration. Neptune's outward journey in the early solar system, as described by the Nice model, shows that giant planets do not always stay where they formed. Many exoplanetary systems appear to have undergone similar reshuffling, with Neptune-like planets moving inward or outward due to gravitational interactions. Studying Neptune's migration provides a template for understanding these processes in other systems. The study of exoplanets also raises new questions about Neptune itself. For instance, many exoplanets of similar size orbit much closer to their stars than Neptune does to the Sun. These hot Neptunes are bombarded with intense radiation, causing their atmospheres to expand or evaporate. By comparing them to cold Neptune in our own system, scientists can explore how environment shapes planetary evolution. Why did our Neptune survive with its atmosphere intact, while many close-in exoplanets seem to lose theirs? The contrast offers valuable insights into atmospheric escape and long-term stability. In the coming years, telescopes like the James Webb Space Telescope and future observatories will continue to study exoplanets in the Neptune size range, searching for atmospheric signatures and refining mass and radius measurements. Every new piece of data will circle back to Neptune, grounding the interpretations in what we know about this icy world. Far from being an isolated curiosity, Neptune is becoming a linchpin in the quest to understand planets beyond the solar system. Despite its importance, Neptune remains one of the least explored planets in our solar system. To date, only one spacecraft, Voyager 2, has flown past it, and that was in 1989. The encounter lasted only a matter of hours, yet it revealed a world filled with storms, strong winds, unusual magnetic fields, faint rings, and an active moon, Triton. In the decades since, astronomers have relied solely on telescopes to study Neptune, leaving huge gaps in our knowledge. The case for sending a dedicated mission to Neptune is therefore extremely strong, both scientifically and technologically. One of the main motivations is Neptune's role as an ice giant. While we have studied gas giants like Jupiter and Saturn in detail, the ice giants remain poorly understood. This is striking because planets similar in size to Neptune appear to be among the most common in our galaxy. To understand exoplanets, we need to understand Neptune itself. A return mission could measure its atmosphere, probe its internal structure, and study its magnetosphere in unprecedented detail, providing a foundation for interpreting observations of countless Neptune-like worlds orbiting other stars. Another compelling reason is Triton. Voyager 2 revealed active geysers erupting on its surface, making it one of the most geologically dynamic moons in the solar system. Triton's retrograde orbit suggests it was captured from the Kuiper Belt, meaning it offers a direct window into that distant region of the solar system. There is also evidence that Triton might harbor a subsurface ocean, raising the tantalizing possibility of habitability. A mission to Neptune would therefore double as a mission to one of the most intriguing moons in the solar system, with the potential for major discoveries about geology, chemistry, and possibly even life. Neptune's rings and smaller moons also remain mysteries. The arcs in its Adam's ring defy easy explanation, and many of its inner moons have only been photographed at low resolution. A spacecraft in orbit around Neptune could track these systems over time, uncovering how they interact and evolve. This would provide new insights into the dynamics of planetary rings and the complex gravitational interplay between moons and their parent planet. From a broader perspective, Neptune is also key to understanding the solar system's history. Its migration in the early solar system likely reshaped the Kuiper Belt and influenced the bombardment of the inner planets. Studying Neptune in detail could help confirm or refine these models, improving our understanding of how planetary systems evolve over billions of years. Technologically, a Neptune mission would be challenging but feasible. The vast distance means long travel times, likely over a decade, and limited power from the sun makes nuclear power sources essential. Communications would also involve long delays, yet missions like Voyager, Cassini, New Horizons, and Juno have shown that we can successfully explore distant worlds. With modern instruments, a Neptune orbiter and Triton lander or probe could revolutionize planetary science. There have already been proposals, such as NASA's Trident concept, which envisioned a flyby of Triton, and more ambitious Neptune orbiter concepts that would conduct years of study. While funding remains uncertain, there is growing support in the planetary science community for prioritizing an ice giant mission in the coming decades. Many argue that after missions to Jupiter, Saturn, and now ongoing exploration of Mars and asteroids, it is time to finally give Uranus and Neptune their turn. A mission to Neptune would not just be about filling in gaps, it would likely deliver surprises. Voyager 2's brief flyby showed us how much we didn't know, from supersonic winds to active geysers. With a sustained mission, we could expect discoveries just as dramatic, reshaping our view of the outer solar system. The case for returning to Neptune is therefore both urgent and exciting, promising a scientific payoff that could rival or even exceed that of earlier planetary missions. Sending a spacecraft to Neptune is not a trivial task. The planet lies almost 30 times farther from the Sun than Earth, meaning that the journey requires immense planning, advanced technology, and significant patience. While the rewards of exploration are great, the obstacles are equally formidable, which is one reason why Neptune remains so little studied compared to other planets. The first and most obvious challenge is distance. Neptune is, on average, about 4.5 billion kilometers, 2.8 billion miles, away from Earth. Even traveling at the tremendous speeds of interplanetary spacecraft, it can take more than a decade to reach. Voyager 2, which launched in 1977, only arrived in 1989 after using gravity assists from Jupiter, Saturn, and Uranus to increase its speed. Any modern mission would also need to use similar techniques, carefully timing its launch to take advantage of planetary alignments that occur only once every few decades. Communication is another challenge. At Neptune's distance, radio signals take about 4 hours to travel one way between Earth and the spacecraft. This means that real-time control is impossible. Missions must be highly autonomous, capable of making decisions and adjustments without waiting for instructions. Building such autonomy into spacecraft requires sophisticated onboard computers and software, which adds complexity and cost. Power is also a critical issue. Solar energy is too weak at Neptune to be practical for spacecraft operations. Instead, missions must rely on nuclear power sources, such as radioisotope thermoelectric generators, RTGs, which convert heat from decaying plutonium into electricity. These power supplies are reliable but expensive and limited in availability, making mission planning dependent on resources outside of engineering alone. The environment around Neptune also poses hazards. Its strong winds and storms create an atmosphere that is dynamic and unpredictable. Any probe sent into Neptune's atmosphere would face extreme pressures and temperatures as they descend, likely surviving only a short time before being crushed. Its magnetosphere and radiation belts, though weaker than Jupiter's, still present dangers to spacecraft electronics, requiring protective shielding. Designing a mission that can conduct meaningful science while surviving these conditions is a major engineering challenge. A flyby, like Voyager 2, is simpler and less risky, but provides only a brief glimpse. An orbiter would offer years of study, but requires enormous amounts of fuel for insertion into Neptune's orbit. Concepts for combining an orbiter with atmospheric probes or landers on Triton push the technological boundaries even further. Each additional objective adds weight, cost, and complexity to an already difficult mission. Funding is another challenge. Outer planet missions are among the most expensive in planetary science, often costing billions of dollars. With limited budgets and competing priorities, missions to Neptune often lose out to more immediate or politically appealing targets, such as Mars or asteroids with commercial potential. Advocates argue that the scientific payoff of a Neptune mission justifies the expense, but convincing decision-makers remains a hurdle. Despite these obstacles, progress is possible. Advances in propulsion, such as solar electric systems or nuclear thermal rockets, could shorten travel times. Improvements in AI and onboard autonomy would allow spacecraft to operate more independently. An international collaboration could help share costs and expertise. Each challenge is significant, but none are insurmountable with the right planning and investment. Ultimately, the challenges of exploring Neptune reflect the limits of our current technology and resources, not the impossibility of the task. Just as the difficulties of reaching Saturn were once daunting, but eventually overcome by missions like Cassini, so too can Neptune's barriers be surpassed. The question is not whether we can explore Neptune, it is when we will decide that the time has come to make the journey. Neptune and Uranus are often considered twin planets because they are similar in size, composition, and position within the solar system. Both are classified as ice giants, a category that distinguishes them from the gas giants Jupiter and Saturn. Yet despite their similarities, the two worlds exhibit striking differences that provide valuable insights into planetary science and the diversity of planetary systems. In terms of size, Uranus is slightly larger in diameter than Neptune, making it the third largest planet in the solar system, while Neptune is the fourth. However, Neptune has more mass, which makes it denser than Uranus. This extra density gives Neptune a stronger gravitational pull and a more compact structure, suggesting differences in how the two planets formed and evolved. Their colors are among their most iconic features. Uranus displays a pale cyan hue, while Neptune is a deeper, more vibrant blue. Both colors are caused primarily by methane in their atmospheres, which absorbs red light and reflects blue. However, Neptune's more intense color indicates that additional factors are at play, possibly related to higher atmospheric activity or the presence of unknown trace gases or aerosols that enhance the deeper blue shade. One of the starkest contrasts lies in atmospheric dynamics. Neptune is home to the fastest winds in the solar system, reaching speeds of up to 2,100 kilometers per hour. These violent winds drive dramatic storms like the Great Dark Spot, making Neptune a restless and energetic world. Uranus, on the other hand, has a much calmer and more subdued atmosphere. Its storms are less frequent and less dramatic, and its winds, while strong, do not rival Neptune's extremes. Scientists theorize that Neptune's internal heat plays a major role in powering its turbulent atmosphere, whereas Uranus radiates very little heat and appears comparatively dormant. The magnetic fields of Uranus and Neptune also show curious similarities and differences. Both planets have highly tilted magnetic fields that are offset from their centers, unlike the neatly aligned fields of Earth or Jupiter. This unusual geometry suggests that their magnetic dynamos are generated in shallow layers closer to the surface, rather than deep in the core. While Uranus's tilt is extreme, almost 98 degrees, making it roll on its side as it orbits. Neptune's tilt is about 28 degrees, more like Earth's. This difference in orientation has profound effects on their seasons and the way sunlight interacts with their atmospheres. Moons provide another area of comparison. Uranus has 27 known moons, many named after characters from Shakespearean plays, while Neptune has 14, dominated by Triton. Triton is larger than all of Uranus's moons and is geologically active, with geysers and a retrograde orbit that suggests it was captured rather than formed alongside Neptune. Uranus's moons, by contrast, show varied geologies but lack the dramatic features of Triton, making Neptune's system more dynamic despite having fewer satellites. Rings also separate the two planets in subtle ways. Both Uranus and Neptune have faint ring systems, but Uranus's rings are darker and narrower, while Neptune's are broader and clumpier, possibly due to gravitational interactions with small moons embedded within them. Neither ring system rivals the grandeur of Saturn's, but both provide clues about planetary history and the role of debris in shaping planetary environments. Comparing Neptune and Uranus highlights how two planets with so much in common can nonetheless evolve in very different ways. Uranus appears quiet, tilted, and understated, while Neptune is dynamic, stormy, and visually striking. Together, they illustrate how even small differences in internal heat, composition, or orbital history can lead to vastly different planetary personalities. Understanding both planets in detail is essential for building a complete picture of ice giants as a class of worlds, and for interpreting similar planets now being discovered in exoplanetary systems across the galaxy. Neptune, as a planetary name, draws directly from Roman mythology. The Romans identified Neptune as the god of the sea, storms, and horses, adapting elements of the earlier Greek deity Poseidon. When astronomers in the mid-19th century needed a name for the newly discovered planet, they chose Neptune because of its deep blue color and its association with water, making the sea god an appropriate namesake. This practice of drawing planetary names from classical mythology followed traditions already set with Mars, Jupiter, and Saturn. In art and literature, Neptune has long been depicted as a powerful figure wielding a trident, commanding the oceans and embodying unpredictability. By naming the planet Neptune, astronomers linked this distant, stormy world to the imagery of untamed seas, underscoring both its mystery and its immense natural power. The choice was quickly accepted internationally, as astronomy during that period was already deeply intertwined with classical education and cultural symbolism. The symbolism of Neptune as the god of the sea resonated beyond its naming. The planet became associated with exploration and the unknown, mirroring humanity's historical relationship with the oceans. Just as Earth's oceans represented uncharted territory to early explorers, Neptune symbolized the frontier of the solar system. In the 19th and 20th centuries, when telescopes and orbital calculations revealed Neptune's existence and position, it became a symbol of scientific triumph over distance and invisibility. The discovery showed that mathematics and observation could uncover hidden worlds, adding a sense of mythic destiny to the science of astronomy. Neptune's presence in popular culture has also been notable. The planet appears in literature, music, and even modern film as a symbol of distance, mystery, and often danger. Gustav Holst included Neptune the Mystic as the final movement of his orchestral suite The Planets, written in the early 20th century. Holst's music reflects the planet's association with mysticism, using ethereal choral passages to suggest something far removed from the ordinary human experience. In literature, Neptune often serves as a setting for science fiction narratives, whether as a destination for exploration or as a distant outpost where human imagination projects new possibilities. Astrology, though not a scientific discipline, has also woven Neptune into its framework since the planet's discovery. In astrological traditions, Neptune is associated with intuition, dreams, illusions, and spirituality, reflecting the planet's mysterious and hard-to-grasp qualities. While not grounded in scientific evidence, these associations have influenced cultural perceptions of Neptune and extended its symbolism into personal and metaphysical domains. The name and imagery of Neptune also appear in other cultural arenas. Naval vessels, submarines, and maritime projects have been named after the god or the planet, emphasizing strength, mystery, and dominion over watery realms. In popular media, Neptune has been portrayed in animation, comics, and novels, often depicted as either a majestic realm or a forbidding frontier. The cultural resonance of Neptune demonstrates how science and myth can intersect. The planet, discovered through mathematics and confirmed by telescopes, nevertheless carries with it an aura of mythological power. It reflects a pattern in human history. When we encounter something vast and unknown, we often turn to stories and symbols to give it meaning. Neptune's scientific identity as an ice giant with powerful winds is now well established, yet its cultural identity as the god of the sea continues to shape how people imagine and engage with it. By blending myth, music, and science, Neptune occupies a unique position in both intellectual and cultural history. It embodies discovery through reason, while also reminding us that imagination and symbolism remain central to how humans interpret the universe. Despite being one of the most fascinating planets in the solar system, Neptune remains one of the least explored. Beyond Voyager 2's brief flyby in 1989 and ongoing telescope observations, no spacecraft has conducted a dedicated mission to study the planet up close. This lack of data leaves huge gaps in our understanding of its atmosphere, magnetic field, moons, and rings. As space agencies set their sights on the outer solar system again, Neptune is increasingly recognized as a prime candidate for exploration. One of the strongest reasons to revisit Neptune lies in its atmosphere. Voyager 2 revealed supersonic winds, dynamic storms, and complex cloud patterns, but with limited resolution and only a brief observational window. Modern instruments could monitor Neptune's weather over years or even decades, tracking how storms form, evolve, and dissipate. This would not only shed light on the mechanics of giant planet atmospheres, but also improve models of exoplanets, many of which resemble Neptune in size and composition. The planet's magnetic field presents another mystery. Neptune's field is tilted about 47 degrees from its axis of rotation and offset from the planet's center, unlike Earth's relatively aligned magnetic field. This suggests unusual interior dynamics that challenge existing models of planetary magnetism. A future orbiter equipped with magnetometers could map the field in detail, offering crucial insights into how such magnetic environments are generated and sustained. Perhaps the most compelling reason to study Neptune lies in its moons, especially Triton. Triton is a captured Kuiper Belt object with retrograde motion and evidence of cryovolcanism. Its surface shows signs of relatively recent geological activity, making it one of the most intriguing bodies in the solar system. Voyager 2 captured geysers of nitrogen erupting from Triton's surface, hinting at internal heat and potentially even subsurface oceans. A dedicated mission could explore Triton in detail, searching for signs of habitability or unique chemical environments. The possibility that a distant icy moon harbors conditions favorable to life adds immense scientific value to any Neptune mission. The rings of Neptune, faint and incomplete, also remain poorly understood. Their composition, age, and relationship to the planet's moons are questions that can only be answered with direct observation. Understanding how such rings form and evolve would add another piece to the puzzle of planetary system dynamics, offering parallels to Saturn's much grander ring system. On the practical side, Neptune exploration is difficult. The planet is extremely distant, requiring more than a decade of travel time with current propulsion technologies. Power sources are limited. Solar panels are ineffective at such distances, making nuclear energy a necessity. Designing a mission that can last decades, endure the harsh conditions of deep space, and still deliver robust science requires significant planning and resources. Despite these challenges, proposed missions have been discussed. NASA and other agencies have considered orbiters, flybys, and probes that could study Neptune and Triton in detail. Many planetary scientists argue that Neptune, more than any other outer planet, holds the keys to understanding ice giants both in our system and beyond. Since exoplanet surveys show that Neptune-like planets are among the most common types in the galaxy, studying our own local example has universal importance. There is also a sense of unfinished business. Voyager 2 provided tantalizing glimpses, but left too many unanswered questions. With modern technology, high-resolution instruments, and advanced communication systems, a new mission could transform Neptune from a distant enigma into a well-understood world. Much as Cassini revolutionized our knowledge of Saturn, a dedicated Neptune mission could reshape planetary science. The timing is crucial. As attention shifts toward returning humans to the Moon and eventually reaching Mars, outer planet exploration risks being sidelined. Advocates argue that Neptune should remain on the priority list, both for its scientific potential and for the broader perspective it offers. Exploring the farthest known planet in our solar system reminds humanity of its place in a vast cosmic environment, inspiring curiosity and innovation. Ultimately, the case for Neptune is both scientific and symbolic. Scientifically, it promises to reveal fundamental truths about planetary formation, magnetic fields, moons, and atmospheric dynamics. Symbolically, it represents the frontier of exploration, carrying forward the spirit that led astronomers to predict and discover it in the first place. Neptune is a reminder that even at the far edges of our planetary neighborhood, there are worlds waiting to be explored. The story of Neptune does not end with the planet itself. Its discovery, its properties, and its mysteries all feed into a much larger narrative. How we study the universe, how we discover worlds beyond our reach, and what we learn about the countless planets orbiting other stars. Neptune is both a distant neighbor and a guide to the cosmos. Its very discovery demonstrated the power of mathematics and prediction. Before a telescope confirmed it, scientists inferred its presence from gravitational tugs on Uranus. This approach mirrors how astronomers now find exoplanets by observing the subtle effects they have on their stars. Neptune's discovery was the first great example of detecting a world not by sight, but by careful reasoning. That method has since grown into one of the most successful techniques for expanding our knowledge of the galaxy. Neptune also shows us that size and composition matter. Unlike Jupiter or Saturn, it did not become a gas giant. Unlike Earth or Mars, it did not remain rocky. Its intermediate structure places it in the ice giant category, a class that appears extremely common in exoplanet surveys. When astronomers look out into space, they find that Neptune-like planets are among the most frequent planetary types. Studying Neptune is therefore not just about understanding our solar system, it's about understanding one of the universe's favorite designs. The planet's weather systems, magnetic field, and internal heat remind us of how dynamic and surprising planets can be. Winds faster than sound, magnetic fields tilted and offset, and mysterious sources of internal energy all point to complexities that even our best models struggle to capture. This suggests that exoplanets, too, may harbor features far stranger than we currently imagine. Neptune warns us to stay humble, to expect the unexpected when exploring the unknown. Triton, Neptune's largest moon, extends the lesson further. A captured Kuiper Belt object, it demonstrates how planetary systems can reshape themselves over time, pulling in wandering bodies and creating new arrangements. Its potential cryovolcanism and subsurface ocean also highlight how life's potential habitats are not limited to warm, rocky planets. Instead, icy moons at the fringes of star systems may hold the right conditions for chemistry and biology. Neptune, through Triton, reminds us that the search for life must remain broad. Finally, Neptune teaches us about persistence and patience. It took centuries for humans to realize it was a planet, decades for a spacecraft to visit, and it may take more decades before another mission returns. Its distance and difficulty demand long-term commitment, yet this very challenge mirrors the nature of exploration itself. Discovering and understanding distant worlds is a slow process, but it expands our vision, generation by generation. In this way, Neptune represents both a destination and a symbol. It stands at the frontier of our solar system, distant and stormy, yet waiting with answers that could reshape how we see planetary science, exoplanets, and even the possibilities for life. By studying Neptune, we are not just learning about a single planet. We are practicing how to study the universe itself. When Neptune is placed within the wider context of the solar system, its importance becomes clearer. Each planet contributes a different perspective on planetary formation and evolution, and Neptune's story is particularly significant because it represents the outer edge of what we traditionally call the planetary family. Its position, structure, and influence on nearby objects make it not just another member of the solar system, but a keystone in understanding how the system as a whole functions. Compared to the inner rocky planets, Neptune is vastly different in scale and composition. Mercury, Venus, Earth, and Mars are made mostly of rock and metal, while Neptune is primarily hydrogen, helium, water, ammonia, and methane. This distinction reveals a natural divide in the solar system: smaller terrestrial planets close to the Sun, and larger gaseous or icy planets farther out. Studying Neptune helps explain why the solar system divided this way, showing how distance from the Sun determines what materials could condense and accumulate during formation. In comparison to Jupiter and Saturn, Neptune demonstrates the limits of gas giant growth. Jupiter and Saturn captured enormous amounts of hydrogen and helium, becoming the largest planets, while Neptune and Uranus are smaller and richer in heavier ices. This suggests that timing and position in the early solar nebula determined their final structures. Neptune may have formed later than Jupiter and Saturn, missing the chance to capture more hydrogen before the nebula dispersed. This timing difference is a clue to how planets evolved differently within the same system. Neptune's gravitational role also ties into the broader solar system architecture. It helps define the outer edge of the planetary zone, while also shaping the Kuiper belt and influencing comets that pass near Earth. Without Neptune's stabilizing and shepherding effects, the outer solar system might look very different, and the delivery of icy materials to the inner planets may have been less efficient. In that sense, Neptune's presence is linked to conditions that eventually influenced Earth's environment. When compared to Uranus, Neptune offers a kind of sibling contrast. The two ice giants are similar in size and mass, but their atmospheres, weather systems, and magnetic fields differ in striking ways. Neptune's storms are stronger and more visible, and its internal heat is more active. This contrast shows how two planets with comparable bulk properties can diverge significantly due to differences in internal dynamics or history. By studying both together, scientists can narrow down which factors are most critical in shaping a planet's behavior. Placed within the solar system as a whole, Neptune highlights both variety and unity. It shares traits with other planets, but also demonstrates extremes, such as the fastest winds or one of the most unusual magnetic fields. By including Neptune in planetary studies, we get a more complete spectrum of planetary types, from rocky to gaseous to icy. This full spectrum is necessary to understand planetary science, not only in our solar system, but also in exoplanetary systems across the galaxy. The story of Neptune does not end with the planet itself. Its discovery, its properties, and its mysteries all feed into a much larger narrative: how we study the universe, how we discover worlds beyond our reach, and what we learn about the countless planets orbiting other stars. Neptune is both a distant neighbor and a guide to the cosmos. Its very discovery demonstrated the power of mathematics and prediction. Before a telescope confirmed it, scientists inferred its presence from gravitational tugs on Uranus. This approach mirrors how astronomers now find exoplanets by observing the subtle effects they have on their stars. Neptune's discovery was the first great example of detecting a world not by sight, but by careful reasoning. That method has since grown into one of the most successful techniques for expanding our knowledge of the galaxy. Neptune also shows us that size and composition matter. Unlike Jupiter or Saturn, it did not become a gas giant. Unlike Earth or Mars, it did not remain rocky. Its intermediate structure places it in the ice giant category, a class that appears extremely common in exoplanet surveys. When astronomers look out into space, they find that Neptune-like planets are among the most frequent planetary types. Studying Neptune is therefore not just about understanding our solar system. It's about understanding one of the universe's favorite designs. The planet's weather systems, magnetic field, and internal heat remind us of how dynamic and surprising planets can be. Winds faster than sound, magnetic fields tilted and offset, and mysterious sources of internal energy all point to complexities that even our best models struggle to capture. This suggests that exoplanets too may harbor features far stranger than we currently imagine. Neptune warns us to stay humble, to expect the unexpected when exploring the unknown. Triton, Neptune's largest moon, extends the lesson further. A captured Kuiper Belt object, it demonstrates how planetary systems can reshape themselves over time, pulling in wandering bodies and creating new arrangements. Its potential cryovolcanism and subsurface ocean also highlight how life's potential habitats are not limited to warm, rocky planets. Instead, icy moons at the fringes of star systems may hold the right conditions for chemistry and biology. Neptune, through Triton, reminds us that the search for life must remain broad. Finally, Neptune teaches us about persistence and patience. It took centuries for humans to realize it was a planet, decades for a spacecraft to visit, and it may take more decades before another mission returns. Its distance and difficulty demand long-term commitment. Yet this very challenge mirrors the nature of exploration itself. Discovering and understanding distant worlds is a slow process, but it expands our vision, generation by generation. In this way, Neptune represents both a destination and a symbol. It stands at the frontier of our solar system, distant and stormy, yet waiting with answers that could reshape how we see planetary science, exoplanets, and even the possibilities for life. By studying Neptune, we are not just learning about a single planet, we are practicing how to study the universe itself. Studying Neptune has always meant grappling with the limits of what human tools can achieve. Its great distance from Earth places it far beyond the reach of casual observation, and even with today's best instruments, it remains a challenging target. Unlike the brighter and closer planets, Neptune requires long exposure times, precise optics, and creative techniques to reveal its details. In many ways, Neptune is a reminder of how much the universe resists easy understanding, and how much effort is required to pull faint signals out of the noise of distance. Before the invention of powerful telescopes, Neptune was indistinguishable from a star. Even after its discovery, early astronomers struggled to study its features. Its small apparent size in the sky, never more than a tiny blue disk, meant that little could be resolved. The invention of larger telescopes improved matters, but the atmosphere of Earth itself presented a barrier. Turbulence in the air distorts light, blurring the image and limiting what can be seen. For most of history, Neptune was more an object of calculation than of direct visual study. The advent of space telescopes changed this picture. The Hubble Space Telescope offered clearer views, free from atmospheric interference. With Hubble, astronomers began to track Neptune's cloud patterns, observe storm systems, and refine measurements of its rings. Later, adaptive optics systems on ground-based observatories like Keck in Hawaii allowed telescopes on Earth to correct for atmospheric distortion in real time, further sharpening the image of Neptune. These methods transform Neptune from a blur into a dynamic world with visible weather, though even now the resolution remains limited compared to what a spacecraft could achieve. The James Webb Space Telescope has added another layer of capability. Its infrared instruments can detect heat patterns and probe Neptune's atmosphere in ways not possible before. Early JWST images have provided detailed views of Neptune's rings and revealed atmospheric structure with unprecedented clarity. Yet even with JWST, Neptune remains a challenge. The planet is faint, distant, and requires careful planning to study without being overwhelmed by the brightness of nearby objects. This limitation underscores why spacecraft exploration is so important. Telescopes can provide snapshots, but they cannot orbit, measure fields directly, or capture continuous data at close range. Voyager 2's flyby remains the only instance in which humanity has directly studied Neptune up close, and it revealed more in a matter of days than centuries of Earth-based observation could. Until a new mission is launched, Neptune will remain partially hidden behind the veil of distance, a reminder of the technological gap between what we want to know and what we are currently able to measure. Yet there is value in that limitation. Pushing against the boundaries of observation has driven innovation, from adaptive optics to advanced space telescopes. Neptune, by being difficult, has forced astronomers to invent new ways of seeing. Each small advance in resolving its clouds or measuring its magnetic field has also advanced the tools we use across astronomy, from studying distant galaxies to imaging exoplanets. Neptune's remoteness thus serves not only as an obstacle, but also as a catalyst for progress. In this way, Neptune teaches us something profound about science itself. Knowledge is not always easy or direct. Sometimes it comes in fragments, blurred images, or faint signals. Extracting meaning requires persistence, creativity, and new inventions. Neptune's story is not just one of planetary science, but also one of human ingenuity, proving that even the most distant worlds can yield secrets when observed with patience and determination. When considering the possibility of life beyond Earth, Neptune itself may not seem like a candidate. Its atmosphere is composed largely of hydrogen, helium, and methane, with pressures and temperatures that would destroy complex molecules and living systems as we know them. The winds roar at supersonic speeds, the cold is extreme, and the lack of a solid surface makes the idea of habitability implausible. But while Neptune itself is not a place to expect life, its system, particularly its largest moon, Triton, opens up intriguing possibilities. Triton is one of the most remarkable bodies in the solar system. Captured from the Kuiper belt, it orbits Neptune in the opposite direction of the planet's rotation, making it dynamically unusual and evidence of a complex past. When Voyager 2 flew by in 1989, it observed geysers of nitrogen erupting from the surface, proof that the moon is geologically active. This activity suggests the presence of internal heat, which in turn raises the possibility of a subsurface ocean beneath Triton's icy crust. If such an ocean exists, it could represent a stable environment where chemical reactions might support microbial life. The concept of life in icy oceans is not unique to Triton. Other moons in the solar system, such as Europa around Jupiter and Enceladus around Saturn, are strong candidates for habitable environments beneath ice layers. Triton adds to this list, expanding the range of places where life could exist. If life can survive in these hidden oceans, it would reshape our understanding of habitability. The lesson is that life might thrive, not only on warm, Earth-like worlds, but also in cold, dark environments where liquid water is protected beneath ice. Neptune itself contributes to this perspective by being part of the family of ice giants. Exoplanet surveys reveal that Neptune-like planets are among the most common types in the galaxy. While their thick atmospheres and high pressures may not host life, their systems of moons could. If many Neptune-like exoplanets also capture icy bodies similar to Triton, then habitable niches could be widespread across the universe. Studying Neptune's system, therefore, informs astrobiology by showing how outer planets and their moons can create environments where life is at least possible. There is also an indirect way in which Neptune links to the question of life. By shaping the Kuiper Belt and influencing the orbits of comets, Neptune has played a role in delivering icy material to the inner solar system. Comets contain water, organics, and other key ingredients for life. If Neptune's gravitational influence helped direct these materials toward Earth billions of years ago, it could have indirectly contributed to the emergence of life on our planet. In this sense, Neptune may be a guardian of habitability, shaping the flow of cosmic materials in ways that supported the conditions for biology on Earth. Exploring Triton and Neptune's system further would provide an important test of these ideas. If a future mission could confirm the presence of a subsurface ocean on Triton, analyze its chemistry, or detect ongoing cryovolcanism, it would bring astrobiology into the outer solar system. Even if no life is found, learning whether such environments are common or rare would refine the search for biosignatures elsewhere. Neptune's system reminds us that the search for life cannot be limited to planets that resemble Earth. It must extend to unexpected, hidden places where conditions may be very different, but no less significant. Neptune holds a place in science, but it also carries weight as a symbol of human ambition. When astronomers in the 19th century predicted its existence through mathematics, they showed that reason and calculation could uncover unseen worlds. This discovery became a triumph of intellect, demonstrating that humanity could reach across billions of kilometers with nothing more than logic, persistence, and curiosity. Neptune thus became more than a planet. It became proof of what the human mind can achieve. Its distance has always reinforced this symbolism. Neptune is not visible to the naked eye, and for most of history it remained hidden. Its position at the frontier of the solar system makes it a natural metaphor for the limits of our reach. Only once has a spacecraft flown by, and even then the encounter lasted just a few days. That fleeting glimpse revealed storms, rings, and moons enough to transform our understanding, but not enough to answer all the questions. Neptune remains a reminder that there are always horizons beyond what we have explored, waiting for the next generation of tools and explorers. In culture and imagination, Neptune is often tied to the sea, storms, and the unknown. The Roman god for whom it was named wielded power over the unpredictable forces of water. By extension, the planet Neptune carries the same aura of unpredictability and strength. Its storms, magnetic field, and captured moon mirror this identity, reinforcing its association with turbulence and mystery. Humanity has often looked to the ocean as a symbol of exploration, and Neptune extends that tradition into the cosmos. As technology advances, Neptune stands as both a challenge and an inspiration. It challenges us because of its distance, its faint signals, and the long time scales needed for missions to reach it. But it inspires us for the same reasons, embodying the spirit of reaching beyond what seems practical or easy. Neptune invites us to think in terms of decades and generations, to imagine projects whose results will be enjoyed by those who come after us. This kind of forward-looking exploration is part of what defines humanity at its best. Neptune also reminds us that science and imagination are not separate. Its discovery was born from mathematics, yet its identity is enriched by mythology, music, and culture. It has been represented in orchestral suites, in art, and in stories, showing how scientific objects also live in the human imagination. When we study Neptune, we are not just analyzing data. We are also engaging with a cultural symbol of mystery, power, and the allure of the unknown. In the end, Neptune embodies the intersection of intellect and wonder. It shows that science is not only about answers, but also about questions that extend our vision of the universe. Its storms, its tilted magnetic field, its strange moon, and its faint rings all remind us that the cosmos is richer and more complex than we expect. Neptune challenges us to keep exploring, to keep asking, and to keep imagining what lies beyond. As the outermost planet in the solar system, Neptune stands as a frontier. It is both real and symbolic, both a physical world and an idea that pushes us further. When humanity finally returns to study it up close, the journey will not only deepen our knowledge of planets, but also reaffirm why we explore it all. Neptune is science, but it is also a mirror of our own spirit, restless, searching, and unafraid of the distance. In summary, Neptune, the eighth and most distant planet of our solar system, is a world of mystery, beauty, and extremes. Though hidden in the cold, dark reaches of space nearly 3 billion miles from Earth, it has captured the curiosity of scientists and dreamers alike. This distant giant was the first planet discovered through mathematics rather than direct observation, a triumph of human intellect in the mid-19th century that changed the way astronomy was done forever. Uranus, discovered only decades earlier, was found to move in ways that could not be explained by Newtonian predictions alone. The unexplained deviations suggested that another unseen planet was exerting its gravitational influence. French mathematician Urbain Le Verrier and British mathematician John Couch Adams both calculated where this new body should be. And in 1846, German astronomer Johann Gottfried Galle pointed his telescope to the predicted region of the sky. There it was, Neptune, just a degree from Le Verrier's calculated position. This moment was more than a discovery. It was a proof of concept that mathematics could guide astronomy into unseen realms. Since its discovery, Neptune has remained a challenge to study. Its enormous distance makes it faint, and only the most powerful telescopes can capture detailed images. For much of the late 19th and 20th centuries, astronomers relied on ground-based telescopes, peering at the blue disk and gradually teasing out details about its size, orbit, and atmosphere. It wasn't until the space age, and particularly the flyby of Voyager 2 in 1989, that Neptune was truly revealed in vivid detail. Voyager 2 remains the only spacecraft to visit Neptune, and its data transformed the planet from a dim smudge in the telescope into a dynamic, turbulent world full of weather systems, fast winds, strange moons, and faint rings. The iconic images of the Great Dark Spot, a massive storm system reminiscent of Jupiter's Great Red Spot, showed that even this cold and distant world is alive with activity. Neptune's physical properties highlight its uniqueness among the outer planets. With a diameter of about 49,000 kilometers, it is slightly smaller than Uranus, yet more massive, giving it a greater density. This suggests a different internal composition and structure. Like Uranus, it is classified as an ice giant rather than a gas giant like Jupiter and Saturn. Its composition includes a large fraction of ices, materials like water, ammonia, and methane in frozen or fluid forms, mixed with hydrogen and helium. Deep within, Neptune likely possesses a rocky core surrounded by a hot, dense fluid mantle of water, methane, and ammonia. Above this lies its thick atmosphere, where methane absorbs red light and gives the planet its striking blue color. The intensity of the hue, deeper than Uranus's pale cyan, may also be influenced by unknown atmospheric constituents that remain under investigation. The atmosphere of Neptune is one of its most fascinating features. Despite its distance from the Sun and its frigid temperatures, averaging around minus 214 degrees Celsius, Neptune is surprisingly active. It possesses the fastest winds in the solar system, reaching speeds over 1,500 miles per hour. This is a paradox. How can a planet receiving such little solar energy generate such furious atmospheric motions? The answer seems to lie in Neptune's internal heat. Unlike Uranus, which radiates little more energy than it receives from the sun, Neptune emits more than twice the energy it absorbs. This internal source fuels its storms and drives its dynamic weather systems. The great dark spot spotted by Voyager 2 was the most dramatic. Example, a storm roughly the size of Earth, surrounded by bright white methane clouds. Though the storm later vanished, replaced by others observed by the Hubble Space Telescope, its existence demonstrated that Neptune's atmosphere is a restless stage of constantly shifting patterns. The magnetosphere of Neptune is another oddity. Tilted at about 47 degrees from its rotational axis and offset from the planet's center, Neptune's magnetic field is among the most irregular in the solar system. Like Uranus, this unusual geometry suggests that the dynamo generating the magnetic field is not located deep in the core, as on Earth, but rather in a shallower shell of conductive fluids. This contributes to an irregular, asymmetric magnetosphere that interacts with the solar wind in unique ways, producing auroras and magnetic variations that continue to intrigue scientists. Neptune is not alone in its journey around the Sun. It is orbited by a collection of moons, each with their own distinct identities. The largest, Triton, is a world that has captivated planetary scientists since Voyager's flyby. Unlike most large moons, Triton orbits in a retrograde direction opposite to Neptune's rotation, strongly suggesting it was once a captured object, possibly a dwarf planet from the Kuiper Belt. Triton is geologically active, with cryovolcanoes and geysers that spew nitrogen gas into space, leaving dark streaks across its surface. It is one of the coldest places in the solar system, yet still dynamic, a place where ices behave like fluids under the low temperatures and pressures. Voyager's images of Triton revealed cantaloupe-like terrain, smooth plains and strange ridges, hinting at a complex geological history. Triton alone is reason enough for future missions to Neptune, as it is likely one of the most intriguing bodies beyond Pluto. In addition to Triton, Neptune has over a dozen smaller moons, most of which are irregularly shaped and likely captured objects. Some, like Proteus, are heavily cratered, while others are tiny and irregular, remnants of the chaotic processes of capture and collision that shaped Neptune's system. Alongside its moons, Neptune also possesses a faint ring system, discovered in 1984 and confirmed by Voyager 2. Unlike Saturn's brilliant rings, Neptune's are tenuous, dark, and incomplete, with bright clumps called ring arcs. These arcs, defying expectations of how rings should behave, may be stabilized by small moonlets embedded within them. Together, Neptune's rings and moons create a dynamic environment shaped by gravity, capture, and the subtle dance of orbital mechanics. Neptune's influence extends far beyond its immediate system. It plays a critical role in shaping the structure of the Kuiper Belt, the vast region of icy bodies beyond Pluto. Many objects are trapped in orbital resonances with Neptune, their movements governed by its gravity. Pluto itself is in a 3-to-2 resonance, completing 2 orbits of the Sun for every 3 of Neptune's. Without Neptune's gravitational shepherding, the outer solar system would look very different. In fact, Neptune's migration in the early solar system may have been responsible for scattering Kuiper Belt objects and shaping the distribution of small bodies we see today. The planet is thus not merely a distant blue orb, but a fundamental architect of the solar system's outer regions. Culturally and symbolically, Neptune has also carried weight. Named after the Roman god of the sea, it embodies mystery, depth, and the unknown. Its deep blue color reinforces this association, evoking the endless oceans of Earth. In astrology and literature, Neptune often symbolizes dreams, illusions, and the subconscious, a fitting metaphor for a planet so distant and elusive that it was long invisible to human eyes. Its discovery through calculation rather than direct observation further enhances its aura of mystery, as if it was revealed not through sight, but through thought and imagination. Despite all we have learned, Neptune remains largely unexplored. Voyager 2 provided a fleeting glimpse, but no mission has returned since. Telescopes like Hubble and more recently, the James Webb Space Telescope have added details, observing storms and atmospheric variations, but the planet still hides countless secrets. Future missions have been proposed, ranging from orbiters to flybys, with special interest in Triton as a potential ocean world beneath its icy shell. The scientific rewards of returning to Neptune would be immense, offering not only a closer look at the planet itself, but also insights into exoplanets. Many of the Neptune-sized planets discovered around other stars, so-called hot Neptunes and mini-Neptunes, are among the most common exoplanet types. Understanding our own Neptune provides a template for interpreting these distant worlds. As scientists continue to analyze Neptune, its energy balance remains one of the most intriguing puzzles. Unlike Uranus, which seems strangely inert, Neptune radiates more than twice the energy it receives from the Sun. This extra heat drives its violent storms and high-speed winds, but the source of that energy is still debated. One possibility is leftover heat from its formation, slowly leaking from the interior. Another theory is that Neptune has more efficient processes for transporting internal heat to the surface, such as convection in its mantle. A third explanation suggests that chemical differentiation within the planet, such as the sinking of heavier elements, releases gravitational energy that is converted into heat. Regardless of the exact mechanism, the result is an atmosphere more dynamic than any other in the outer solar system, a world that defies expectations by being more active the farther it lies from the Sun. The storms of Neptune are a defining feature of this dynamism. Voyager 2 revealed the Great Dark Spot, a high-pressure system similar to Jupiter's Great Red Spot, but smaller and shorter-lived. Hubble later discovered that such storms appear and disappear within a matter of years, making Neptune's atmosphere a restless and changing environment. These storms are often accompanied by bright white methane ice clouds, formed when gases rise and cool, condensing into crystals high above the planet's surface. The rapid evolution of these features underscores Neptune's reputation as a dynamic, unpredictable world. On Earth, weather is influenced primarily by solar heating, but Neptune demonstrates that internal energy can dominate atmospheric behavior, producing winds that howl across the planet at supersonic speeds. The winds themselves are astonishing. At over 1,500 miles per hour, they are the fastest measured in the solar system, far exceeding hurricanes on Earth or jet streams on Jupiter. The paradox of such fast winds on such a cold planet continues to challenge researchers. These winds circle the planet in alternating bands, driven by deep atmospheric circulation and influenced by the planet's rotation. Neptune's day lasts about 16 hours, and this rapid spin helps organize its turbulent atmosphere into zones and belts. The interplay of rotation, internal heat, and atmospheric chemistry produces a planet where, paradoxically, stillness is never an option. Even in the darkness of the outer solar system, Neptune is a place of motion and change. Beyond its atmosphere, Neptune's magnetosphere presents further mysteries. Like Uranus, Neptune's magnetic field is tilted dramatically from its rotational axis and offset from the planet's center. This irregular geometry makes its interactions with the solar wind highly unusual. The magnetosphere stretches and warps in ways that differ from Earth's more symmetrical structure, creating complex auroras and radiation belts. Voyager 2's measurements indicated that the source of the field is likely in a conductive layer of ionized water and ammonia, located relatively close to the surface compared to Earth's deep core dynamo. This shallower dynamo may explain the irregular tilt and offset, but the details remain unresolved. Studying Neptune's magnetosphere is more than planetary science. It has broader implications for understanding magnetic fields in other worlds, including exoplanets that share Neptune's size and composition. One of the most captivating aspects of Neptune's system is Triton, its largest moon. Triton stands apart not only because of its retrograde orbit, but also because of its active surface. Voyager 2's discovery of nitrogen geysers spewing material kilometers into space was astonishing, suggesting ongoing geological activity on a world once thought to be frozen and inert. Triton's thin atmosphere, composed mostly of nitrogen with a trace of methane, is tenuous yet dynamic, with seasonal changes as the Moon orbits Neptune. Its cantaloupe terrain, smooth volcanic plains, and icy ridges reveal a history of resurfacing, while its geysers hint at internal heat, possibly maintained by tidal interactions or the decay of radioactive elements. Triton may even harbor a subsurface ocean, placing it in the intriguing category of ocean worlds alongside Europa, Enceladus, and potentially Pluto. If true, Triton could be one of the most promising locations in the outer solar system for the search for life. The rest of Neptune's moons, though smaller, offer their own insights. Proteus, the second largest, is irregular and heavily cratered, shaped more like a lump than a sphere. Nereid follows a highly eccentric orbit, perhaps evidence of past gravitational interactions when Triton was captured. Many of Neptune's other moons are small, irregular, and likely captured Kuiper Belt objects, relics of the chaotic early solar system. Together, they form a diverse collection that speaks to Neptune's gravitational reach and the violent processes that shaped its neighborhood. The dynamics between Triton, the smaller moons, and Neptune's faint rings highlight the complex interplay of gravity and motion that defines the outer solar system. Those rings, though faint, are equally fascinating. When first detected, they puzzled astronomers because they seemed incomplete, appearing as arcs rather than full circles. Voyager 2 confirmed that Neptune's rings are indeed clumpy, with brighter segments stabilized by the gravitational influence of nearby moons. The main rings, named atoms, Leverrier, Lassell, and Gall, are dark and thin, composed of dust and ice. Unlike Saturn's reflective splendor, Neptune's rings are subtle, nearly invisible except in backscattered light. Their arcs are particularly intriguing, as traditional physics suggests such features should disperse quickly, yet they persist, apparently shepherded by small moons such as Galatea, which help maintain their structure. This delicate balance of forces between rings and moons provides a natural laboratory for studying orbital mechanics and ring dynamics, concepts that extend to astrophysics and the study of other planetary systems. Neptune's role in shaping the outer solar system cannot be overstated. As it migrated outward in the early days of planetary formation, its gravity scattered countless icy bodies, sculpting the Kuiper Belt and populating regions with resonant orbits. Many Kuiper Belt objects remain locked in orbital relationships with Neptune, completing predictable patterns that reveal the planet's gravitational influence. Pluto is the most famous of these, in a 3-to-2 resonance with Neptune, but countless smaller bodies follow similar paths. Neptune's migration may have even been responsible for delivering water and organics to the inner solar system, indirectly influencing the conditions that made life on Earth possible. In this sense, Neptune is not just a distant blue giant, it is a hidden architect of planetary history. The scientific importance of Neptune extends far beyond our solar system. With the discovery of thousands of exoplanets, astronomers have found that Neptune-sized worlds are among the most common in our galaxy. Many of these planets orbit close to their stars, creating classes of hot Neptunes and mini-Neptunes unknown in our solar system. By studying our own Neptune, scientists gain a vital reference point for interpreting these alien worlds. Its composition, atmosphere, magnetosphere, and moons all provide analogs that can be used to model exoplanets. For example, the question of why Neptune emits so much heat informs models of energy balance in exoplanets. Its irregular magnetic field provides clues about how planetary dynamos operate. Its storms and winds serve as a reminder that even cold planets can host active, evolving atmospheres. In short, Neptune is a Rosetta Stone for understanding a vast population of exoplanets. Looking ahead, the exploration of Neptune remains a priority for planetary science. Proposals for orbiters and flybys have circulated for years, with the dual goals of studying Neptune itself and conducting a close examination of Triton. Triton, with its potential subsurface ocean, stands out as a prime target for astrobiology. An orbiter could study its geysers, map its surface in detail, and search for chemical signatures of habitability. At the same time, such a mission would answer long-standing questions about Neptune's atmosphere, magnetic field, and rings. Advances in propulsion and miniaturization of instruments may make such a mission feasible in the coming décennies, though the challenge of distance and cost remains formidable. Yet the scientific payoff, unlocking the secrets of a planet that influences the entire outer solar system, would be immense. From a cultural perspective, Neptune continues to symbolize mystery and the unknown. Its blue color, its association with the sea, and its distance from the sun make it a natural metaphor for exploration into uncharted waters. In literature, film, and even music, Neptune often represents the edge of human understanding, the frontier where imagination and science meet. Its discovery through calculation, rather than direct observation, reinforces this aura, suggesting that some truths are hidden until reason illuminates them. For students of science, Neptune stands as a reminder that the universe still contains realms we have barely glimpsed, waiting for future generations to explore. As we draw closer to the end of Neptune's story, it becomes clear that the planet is more than just a cold, distant giant. It is a case study in planetary science, a living laboratory where every feature, from its internal heat to its tilted magnetic field, forces scientists to reconsider assumptions about how planets work. Unlike Jupiter and Saturn, which dominate with sheer size and bright, obvious features, Neptune reveals its secrets more reluctantly, challenging observers with faint rings, unpredictable storms, and subtle interactions between its moons and arcs. This makes Neptune both frustrating and inspiring. Frustrating because of how little we have seen, and inspiring because of how much is left to learn. The challenges of studying Neptune begin with its sheer distance. At nearly 4.5 billion kilometers, or about 2.8 billion miles, from Earth, signals from a spacecraft take over 4 hours to arrive, and light itself takes more than 4 hours to make the journey. Observing Neptune through Earth's atmosphere is difficult, as its disk is small and faint, easily blurred by atmospheric turbulence. Only with modern adaptive optics and the power of space telescopes like Hubble and the James Webb Space Telescope have astronomers begun to resolve Neptune's details from afar. Even then, what we see is partial and fleeting. A storm here, a haze layer there, hints of seasonal change across decades. To truly understand Neptune, humanity must eventually go there again. Voyager 2, with its brief flyby, provided a glimpse, but only a sustained orbital mission can reveal the deeper truths of this faraway world. The question of habitability often arises in discussions of outer solar system bodies. While Neptune itself is inhospitable, with crushing pressures, extreme cold, and violent winds, its largest moon, Triton, has qualities that spark interest. Triton's geysers demonstrate that energy flows beneath its icy surface. Models suggest that a subsurface ocean may exist, warmed either by radioactive decay or residual tidal heating. Such oceans, sealed beneath kilometers of ice, could be chemically rich and potentially habitable. If life exists elsewhere in our solar system, Triton joins Europa and Enceladus as a candidate. The discovery of such life, even microbial, would transform humanity's understanding of biology and the uniqueness of Earth. Thus, Neptune's system holds not just planetary mysteries, but potentially answers to questions about life in the universe. Beyond habitability, Neptune forces us to expand the boundaries of comparative planetology. By comparing it with Uranus, we see how two similar worlds can be profoundly different. Uranus, with its extreme axial tilt, subdued atmosphere, and apparent lack of internal heat, is quiet where Neptune is loud. Why should two ice giants, nearly the same size and composition, behave so differently? The answer may lie in subtle differences in formation, collision history, or internal layering. But until new missions provide more data, the mystery persists. Comparing Neptune with Jupiter and Saturn also highlights the distinction between gas giants and ice giants. Neptune's higher proportion of heavy elements, its lower mass, and its more compact size mark it as fundamentally different in nature. These distinctions are crucial for understanding the diversity of planets in the galaxy, where Neptune-sized exoplanets abound. Neptune also demonstrates the deep interplay between planets and small bodies. Its migration outward shaped the Kuiper Belt, scattering objects and capturing some in resonance. The discovery of Pluto and countless other Kuiper Belt objects can be traced back to Neptune's gravitational reach. Even today, the orbits of trans-Neptunian objects carry the imprint of Neptune's influence. Some astronomers use these patterns as evidence for a hypothetical Planet 9, a still undiscovered body lurking far beyond Neptune. Whether or not Planet 9 exists, the fact that Neptune's gravity continues to shape the outer solar system shows its enduring role as a cosmic architect. Without Neptune, the solar system as we know it would not exist. The technological and logistical hurdles of returning to Neptune are immense. A spacecraft must travel billions of kilometers, requiring advanced propulsion systems or gravity assists to cut travel time. Once there, it must operate in an environment where sunlight is weak, temperatures are frigid, and radiation belts can be harsh. Powering such a mission requires nuclear energy, as solar panels are insufficient at such distances. Communication delays of hours demand a high degree of autonomy in spacecraft systems. Despite these challenges, mission concepts persist. Proposals for orbiters equipped with atmospheric probes, ring studies, and Triton landers have circulated, but none have yet advanced to reality. The sheer difficulty mirrors the potential reward. Unlocking Neptune's substrates would answer fundamental questions about planets, magnetism, atmospheres, and even the potential for life. In terms of broader meaning, Neptune reminds humanity of both our power and our limits. The fact that it was discovered through mathematical prediction is a testament to the reach of human intellect. The fact that we have only visited it once is a reminder of how much lies beyond our grasp. For students of astronomy, Neptune is both a goal and a challenge. It demands persistence, creativity, and long-term vision to explore. It invites each new generation to pick up the thread of curiosity and extend it further into the unknown reaches of the solar system. The story of Neptune is thus not finished. It is merely paused, awaiting the next great mission. At the cultural level, Neptune continues to inspire imagination. Its association with the god of the sea links it to myths of power, mystery, and the unseen depths. Artists, writers, and composers have drawn on its imagery to evoke the unknown. Even in modern times, Neptune serves as a metaphor for exploration, representing the frontier between what is known and what is not. This dual identity, scientific object and cultural symbol, gives Neptune a place in human thought that transcends astronomy. It is not only a planet, but an idea. The idea that there is always more to discover, always another horizon to cross. In reviewing everything that Neptune represents, one comes away with a sense of balance between knowledge gained and mysteries remaining. We know its size, mass, composition, and place in the solar system. We have glimpsed its storms, measured its winds, mapped its rings, and studied its moons. Yet we lack answers to fundamental questions. Why is it so much more dynamic than Uranus? What sustains its internal heat? How do its storms form and dissipate? Does Triton harbor an ocean? And if so, could it support life? These unanswered questions are not failures, but opportunities, points where the story is left open for future chapters. In science, mystery is not the end, but the beginning, and Neptune offers mystery in abundance. Looking outward, Neptune also connects us to the stars. With exoplanet discoveries, we now know that Neptune-like worlds are common. scattered across the galaxy in orbits close and far from their suns. Studying our Neptune provides a key for unlocking their nature. When astronomers analyze the light from distant worlds, searching for methane, water, or heat signatures, they compare it with what we know of Neptune. Each storm photographed, each magnetic field modeled, each moon studied adds to a growing library of knowledge that stretches far beyond the solar system. Neptune, once a faint speck at the edge of human vision, now stands as a bridge to the study of entire galaxies of planets. In the end, Neptune's story is one of contrasts. It is far, yet influential. It is cold, yet dynamic. It is known, yet mysterious. It challenges observation, yet rewards persistence. It stands at the edge of the solar system, yet at the center of planetary science. To speak of Neptune is to speak of the human drive to understand, the willingness to pursue the faintest clues, and the courage to imagine what lies beyond the horizon. It is a story that will not end soon, for as long as questions remain, the planet will continue to call to us across the gulf of space. When considering Neptune's place in the larger cosmic narrative, it becomes clear that its significance goes well beyond the boundaries of the solar system. It represents both a culmination and a gateway. As the last planet discovered, Neptune closed the chapter of the classical solar system, giving humanity a full inventory of its major worlds. Yet it also opened the door to an entirely new domain of discovery, pointing toward the icy frontier of the Kuiper Belt and the even more distant Oort cloud. Neptune is not merely a planet on the edge, but a signpost, showing us that the universe does not end with what we can see, but extends endlessly beyond. Every time we look at Neptune, we are reminded that discovery is a process without limits, and that each answer inevitably leads to more questions. The narrative of Neptune is also a reminder of the collaborative nature of science. Its existence was predicted not by one lone genius, but by the accumulation of observations, calculations, and the willingness of astronomers across nations to look carefully and share results. From Leverrier's calculations to Galileo's confirmation, the discovery of Neptune showed that scientific truth is often the product of collective effort. This lesson is as relevant today as it was in the 19th century. As we plan new missions and interpret new data, Neptune continues to stand as a symbol of what can be achieved when knowledge is pooled and curiosity is united. It is a planet discovered by mathematics, confirmed by telescopes, and awaiting its next great chapter through spacecraft yet to launch. From a scientific standpoint, Neptune illustrates how much we can learn by stretching technology to its limits. The telescopes that spotted its faint blue disk were at the cutting edge of their day. The Voyager 2 flyby pushed the boundaries of spacecraft engineering, delivering images and measurements that stunned scientists and the public alike. Today, the James Webb Space Telescope continues that tradition, resolving Neptune's rings and storms in new detail. Each step requires ingenuity, patience, and the courage to pursue knowledge across immense distances. And each step also reveals how fragile our view remains, dependent on fleeting opportunities and narrow windows of observation. This tension between technological triumph and observational challenge defines Neptune's place in modern science. As technology advances, new questions about Neptune come into sharper focus. Could long-duration spacecraft explore its system in detail? Could atmospheric probes survive its crushing pressures long enough to measure its chemistry? Could orbiters reveal the depth of its storms or the true structure of its magnetic field? These are not idle questions, but active proposals being considered by scientists and space agencies. To reach Neptune requires decades of planning, years of travel, and enormous resources, but the rewards are equally vast. Triton's geysers could be imaged up close. The rings could be mapped in unprecedented resolution. The deep structure of the atmosphere could be measured directly. Each unanswered question provides a justification, and each mystery provides momentum. For the public, Neptune will always hold a special fascination. It is remote yet visible, faint but unmistakably blue through telescopes. Its name, drawn from Roman mythology, ties it to the timeless human connection with the sea and the unknown. To gaze at Neptune is to imagine voyaging across uncharted waters, to picture exploration in its purest form. In art and literature, it has been invoked as a symbol of mystery, change, and the future. In education, it continues to be a gateway for students first learning about planetary science, a world that bridges the familiar and the unknown. Its cultural resonance is as important as its scientific role, for both shape the way people think about exploration. The relationship between Neptune and exoplanets is another area where the planet's importance shines. The majority of exoplanets discovered so far fall into categories close to Neptune in size and mass. While Earth-like planets dominate the public imagination, it is Neptune-like planets that dominate the statistics. Many orbit close to their stars, creating extreme versions of Neptune with scorching atmospheres and exotic chemistry. By comparing these distant worlds with the Neptune in our own backyard, scientists can begin to make sense of their formation, their evolution, and their possible atmospheres. In this sense, Neptune is not just a single planet, but a model, a reference point for understanding the galaxy itself. One of the most profound aspects of Neptune is its reminder of humility. For all our advances, Neptune remains largely unexplored, its mysteries intact. We know its broad strokes, but not its details. Its storms come and go without us seeing. Its rings shift and arc without us measuring. Its moons orbit in ways that hint at deeper stories yet to be told. Each unanswered question reminds us that the universe is vast, and our reach, while growing, is still small. And yet, the fact that we know as much as we do is itself remarkable, a triumph of human curiosity and determination. This balance between humility and achievement gives Neptune its unique place in the solar system. Looking toward the future, the exploration of Neptune may come to symbolize a new age of space science. As humanity considers missions to Mars, bases on the Moon, and telescopes orbiting the Sun, it also looks outward to the giants of the outer solar system. A Neptune orbiter, perhaps paired with a Triton lander, could redefine what we know about planets, magnetism, and habitability. It could serve as the next great step after Cassini's study of Saturn and Galileo's exploration of Jupiter. And it would remind the world that even in an age of advanced computing and interplanetary probes, there are still frontiers that remain as wild and unknown, as they were to the first astronomers with paper and pen. In this way, Neptune is both a destination and an idea, embodying the spirit of discovery that drives science forward. In conclusion, Neptune's story is one of discovery, mystery, and promise. From its mathematical prediction to its fleeting visit by Voyager 2, it has captured the imagination of scientists and the public alike. Its storms, rings, and moons provide endless puzzles. Its role in shaping the outer solar system reveals its influence on planetary history. Its connection to exoplanets extends its significance beyond the solar system, making it a key to understanding worlds across the galaxy. And its future exploration promises discoveries that could reshape what we know about planets and life itself. To speak of Neptune is to speak of curiosity, perseverance, and imagination. It is the farthest planet, yet one that draws us forward, a reminder that in the great ocean of the cosmos, the horizon is never fixed and the journey never ends.